Look at that image for just a moment. A swirling canvas of violet gas and newborn stars. A place where entire solar systems are being born right now. It's beautiful, isn't it? It's the kind of picture we see all the time, and it makes us feel like we understand the cosmos. We go through school, we learn the planets, we memorize that the sun is a star, and we walk away thinking we've got a pretty good handle on the universe. But what if everything you learned was just the barest beginning? What if the most astonishing, the most bizarre, and the most profound truths about space were never mentioned in any classroom? The universe is far stranger, far more wonderful, and infinitely more mysterious than any textbook could ever contain. It holds secrets that defy our basic understanding of physics, realities so vast they are almost impossible to comprehend, and phenomena so beautiful they seem like pure magic. This is the universe that exists just beyond the edge of your education, a hidden cosmos waiting to be discovered. Today, we are going on a journey to uncover that hidden cosmos. We're diving deep into 30 space facts you didn't learn in school. This isn't a rehash of what you already know. This is an expedition into the extraordinary. We will explore worlds where it rains molten glass, dive into the heart of diamond planets, and unravel the mysteries of invisible giants that hold galaxies together. We will confront realities where time and space bend in impossible ways, and where the very fabric of the universe reveals its most astonishing tricks. This is the knowledge that fuels the passion of astronomers and astrophysicists, the mind-bending truths that remind us just how small and yet how incredibly lucky we are to be a part of this grand cosmic story. This is the real story of our universe, a narrative filled with more wonder and surprise than any work of fiction. So get comfortable and prepare to have your mind expanded. We are about to pull back the curtain on a side of space that is rarely seen. A collection of truths so compelling they will fundamentally change how you see the night sky. From the silent, frozen oceans of distant moons to the explosive deaths of stars that seed the galaxy with the very elements of life, each fact is a piece of a puzzle, revealing a universe that is not only vast but also intimately, astonishingly alive with possibility. Let's begin this adventure together and uncover the first of these incredible secrets. Our first hidden truth begins not in some distant galaxy, but with our closest cosmic companion, the Moon. It feels like a permanent, unchanging fixture in our sky, a silent guardian that has witnessed the entire history of life on our planet. But this constancy is an illusion. The Moon is, in fact, slowly leaving us. Right now, as we speak, it is drifting away from Earth at a rate of about 3.8 centimeters every single year. While that might sound like a trivial amount, roughly the same length your fingernails grow in a few months, this tiny, relentless drift has profound consequences that reshape worlds over cosmic time. The mechanism behind this great lunar escape is a celestial tug of war fought with the ocean's very waters. The Moon's gravity pulls on Earth, creating the familiar bulges we know as high tides. But because Earth rotates so much faster than the Moon orbits, our planet's spin actually drags this tidal bulge slightly ahead of the direct line to the Moon. This massive bulge of water then exerts its own gravitational pull, trying to tug the Moon forward in its orbit. Adding energy to the Moon's orbit causes it to spiral outward, moving a little farther away with each passing year. But this cosmic exchange isn't free. The energy that pushes the Moon away has to come from somewhere, and it's stolen from Earth's own rotational momentum. Our planet's spin is gradually, imperceptibly slowing down. This means our days are getting longer, but at an almost unimaginably slow pace. It takes roughly 100,000 years for the length of an Earth day to increase by just a single second. Yet, if we could rewind the clock billions of years, we would find a vastly different Earth-Moon system. Shortly after the giant impact that formed the Moon, our newborn satellite was perhaps only 15,000 miles away, 10 times closer than it is today. The skies would have been dominated by a monstrous moon appearing many times larger, and a day on Earth would have been a frantic 5 or 6 hours long. Looking forward billions of years into the future, this dance continues. As the moon retreats, our days will stretch longer and longer. The delicate balance that creates total solar eclipses, where the moon can perfectly cover the sun, is a temporary and lucky coincidence in cosmic history. In about 600 million years, the moon will have drifted too far away to completely obscure the sun, and total solar eclipses will become a thing of the past, a memory from Earth's vibrant Middle Age. Eventually, Earth's rotation would slow to match the moon's orbital period, creating a stable arrangement, but the sun's own evolution into a red giant star will likely intervene long before that distant future. So the next time you gaze up at that tranquil, silver disk, remember you are looking at a traveler on an epic journey, slowly saying its goodbyes over the course of eons. Think the moon's slow departure is strange. That's merely a slow, gravitational waltz. For a truly bizarre cosmic phenomenon, we travel 26,000 light-years to the heart of our own Milky Way, to a place where the universe seems to be running its own interstellar distillery. There, floating in the darkness near the galactic center, is a colossal cloud known as Sagittarius B2. This isn't just any cloud of gas and dust. It's a giant, floating reservoir of alcohol, containing enough vinyl alcohol to fill billions upon billions of swimming pools. To understand how such an incredible thing is possible, we first need to understand what these molecular clouds are. They are the nurseries of the galaxy, immense regions of cold, sparse gas and dust where the density is just high enough for atoms to link together and form molecules. Think of them as cosmic chemistry sets, vast and dark, where the raw ingredients of new stars and planets slowly come together. In the freezing vacuum of space, dust grains act as tiny laboratories. Single atoms and simple molecules drifting through the cloud occasionally stick to the surface of these microscopic dust particles. Once anchored, they can slide around and meet other atoms, and in the cold, quiet environment, they have the time and the right conditions to link up and form increasingly complex structures. This is how simple molecules like carbon monoxide are formed, and under the right circumstances, this process can build surprisingly intricate organic molecules, including the various types of alcohol found in Sagittarius B2. Now, when we say alcohol, it's crucial to know we're not talking about the kind you'd find in a beer. The cloud contains vinyl alcohol among other organic compounds. Vinyl alcohol is an important precursor to many biological molecules, but it is not consumable by humans. So, while the sheer volume is staggering, the cloud is thousands of times larger than our entire solar system. This is one cosmic cocktail that is utterly undrinkable. Its significance, however, is far greater than any beverage. The existence of such complex organic molecules in space tells us something profound about the universe. The basic chemical building blocks for life are not unique to Earth. They are being forged in the great emptiness between the stars in these gigantic, frigid clouds. Every time a new star system forms from a cloud like Sagittarius B2, it is already seeded with these complex organic compounds. They become part of the protoplanetary disks that swirl around infant stars, and they are eventually delivered to the surfaces of young planets by comets and asteroids. This means that the very chemistry that led to life on our planet may have had its beginnings in clouds just like this one, billions of years before our sun even ignited. So, while we can't raise a glass to this galactic brewery, we can appreciate it for what it truly is. A massive natural factory producing the primordial ingredients from which solar systems, planets, and perhaps even life itself can eventually arise. And while those interstellar clouds are brewing the ingredients for life, another world much closer to home presents us with a meteorological mystery so extreme it defies all earthly logic. Let's turn our attention to Venus, a planet often called Earth's twin due to its similar size and composition, but in reality it is a hellish, toxic inferno. One of its most astonishing secrets is a phenomenon known as superrotation. Imagine a planet that spins so slowly that a single day lasts longer than its entire year. On Venus, one full rotation on its axis takes 243 Earth days, while a trip around the Sun takes only 225. But here is the truly bizarre part. While the planet itself crawls along, its entire thick blanket of an atmosphere is screaming around the globe at a pace that is almost incomprehensible. Hurricane-force winds propel the clouds of sulfuric acid that shroud the planet, completing a full circuit around Venus in a mere 4 Earth days. This means the atmosphere is traveling roughly 60 times faster than the planet's surface is rotating. It's as if the entire sky of Earth was a relentless global hurricane that never made landfall, perpetually circling the globe while the ground below barely moves. The cause of this incredible atmospheric whiplash is a complex puzzle that scientists are still piecing together. The leading theory points to a combination of 2 powerful factors. The first is the immense heat from the Sun. Venus, being closer to our star than Earth, receives a tremendous amount of solar energy. This heat is most intense at the equator, causing the air there to rise violently. As this hot air rushes upward, it begins to flow toward the cooler poles, but the planet's own slow spin is too weak to significantly deflect this flow. Instead, the planet's rotation, combined with the complex thermal tides created by the intense heating of the atmosphere by the Sun, transfers a massive amount of momentum into the air itself. Think of it like stirring a giant global cup of coffee. The energy from the Sun acts like a colossal spoon, continuously stirring the atmosphere, and because the solid planet below offers so little frictional drag, the winds just keep accelerating and accelerating until they reach these phenomenal speeds. This creates a permanent planet-encircling jet stream high in the Venusian sky. The contrast between the sluggish surface and the frantic atmosphere is absolute. If you could stand on the scorching surface of Venus, you would experience a slow, relentless creep from day into night, with the Sun barely seeming to move in the orange, hazy sky. Yet high above you, the cloud tops would be racing past at hundreds of miles per hour, a permanent, silent tempest completely detached from the world below. This superrotation makes Venus a unique laboratory for understanding fluid dynamics and planetary climates, showing us that even in our own solar system, the laws of physics can combine in ways that create phenomena far stranger than anything we experience here on Earth. But for a truly mind-bending display of cosmic extremes, we have to venture beyond the weather of planets and consider the very nature of matter itself. After the cataclysmic supernova explosion of a massive star, what remains is not always a silent black hole. Sometimes the star leaves behind a relic so bizarre, it challenges our fundamental understanding of reality, a neutron star. These are the collapsed cores of stars that were once between about 8 and 20 times the mass of our Sun. When such a star runs out of fuel, its immense gravity causes its core to collapse in a fraction of a second. The force is so unimaginably powerful that it smashes electrons and protons together, fusing them into neutrons and releasing a flood of neutrinos. What was once an object larger than our entire Sun is crushed into a perfect sphere barely the size of a city, typically only about 12 miles across. It is this incredible compression that creates the most staggering property of these objects, their density. To say a neutron star is dense is a profound understatement. A single sugar cube-sized amount of material from a neutron star would weigh approximately 1 billion tons here on Earth. Let's try to wrap our minds around that number. 1 billion tons, that is the weight of every single human being currently alive on our planet, all 7.8 billion of us, compressed into a volume you could hold between your fingers. Or, to use another analogy, imagine taking Mount Everest, the most massive mountain on Earth, and squeezing all of its rock and ice down into a single, heavy paperweight you could place on your desk. This is the level of density we are talking about, where the very atoms that make up matter have been utterly destroyed. Under the intense gravitational pressure, the space that typically exists within an atom completely vanishes. In a normal object, atoms are mostly empty space. If you removed all the vacant space from the atoms in every human on Earth, the entire human race would fit into a volume smaller than a sugar cube. But on a neutron star, this isn't a theoretical exercise, it's the reality. The atomic nuclei are packed together so tightly that they touch, creating a substance that is essentially a giant, solid atomic nucleus. A sea of neutrons so compact that it represents the final state of matter before it collapses into the infinite density of a black hole. The consequences of this density are as dramatic as they are strange. The surface of a neutron star is a perfect, seamless crystalline crust, harder than any diamond, floating atop a superfluid core. Their gravity is so intense that if you were to drop a marshmallow onto the surface from just a meter above, it would impact with the energy of a nuclear bomb, its atoms instantly fused by the unbelievable force. These stars are not just inert relics, many are cosmic powerhouses spinning at dizzying speeds. Some, known as pulsars, rotate hundreds of times per second, sweeping beams of radiation across the galaxy like a lighthouse, their regularity rivaling that of atomic clocks. So, while we often look to black holes as the ultimate cosmic mystery, neutron stars stand as a breathtaking testament to the sheer, raw power of gravity, showing us that the universe can take the familiar stuff of atoms and compress it into a form so extreme it borders on the magical. From the city-sized density of a neutron star, we travel back into our own solar system to witness a different kind of cosmic giant, one that has been raging for centuries. For as long as we have pointed telescopes at Jupiter, we have been captivated by its most famous feature, the Great Red Spot. This colossal, swirling storm is a permanent fixture in the dynamic atmosphere of the gas giant, an anticyclone so vast that, for generations, we have taught that it could comfortably swallow 2 or even 3 Earths side by side. It is a tempest that has likely been churning for at least 400 years, a testament to the sheer scale and energy of Jupiter's weather systems. But this iconic feature is not the immortal behemoth we once thought it was. It is undergoing a dramatic transformation, steadily shrinking before our very eyes, and the reason why remains one of the most compelling puzzles in planetary science. Historical observations from the late 19th century suggest the storm was once truly enormous, perhaps over 25,000 miles across at its widest point, large enough to fit 4 Earths in a row. As recently as the flybys of the Voyager spacecraft in 1979, it still measured about 14,500 miles across, but decades of monitoring from Earth-based telescopes and orbiting spacecraft have revealed a clear and persistent trend. The Great Red Spot is getting smaller. Recent measurements from NASA's Juno spacecraft, which has been providing stunningly detailed images of Jupiter's cloud tops since 2016, show the storm has narrowed to approximately 10,000 miles across. While still large enough to envelop our entire planet, this represents a significant reduction from its historical grandeur. The storm isn't just shrinking in diameter, it's also changing shape, becoming more circular and showing changes in its iconic, rich red color. The question that baffles scientists is why? What could possibly be causing a storm that has persisted for centuries to finally begin to wane? There are several leading theories, but no definitive answers yet. One idea focuses on the interaction between the Great Red Spot and smaller storms and eddies that constantly churn through Jupiter's atmosphere. Juno's data has revealed that the spot is not a simple, isolated vortex. It is a deeply rooted structure that extends hundreds of miles down into the planet's atmosphere, and it is constantly bumping into and absorbing or shearing apart these smaller features. These interactions may be sapping energy from the main storm, acting as a kind of atmospheric friction that is gradually robbing it of its power and size. Another possibility involves internal heat. Jupiter radiates more heat than it receives from the Sun, and this internal energy drives its ferocious jet streams and storm activity. Changes in how this heat is distributed deep within the planet's fluid interior could be altering the very engine that sustains the Great Red Spot, slowly starving it of the convective power it needs to maintain its immense scale. We may also be witnessing a natural, long-term cycle of the storm. Perhaps it shrinks and grows over millennia, and we simply have the privilege of observing one phase of its epic life. The changing color, which can vary from a brick red to a pale salmon hue, is another clue. The exact chemistry that produces the red color is still debated, but it's likely related to compounds being upwelled from deeper in the atmosphere and altered by solar ultraviolet radiation. As the storm's dynamics change, its wind speeds, its temperature, its vertical structure, the chemical recipe for its color may be changing as well. The ongoing saga of the Great Red Spot is a powerful reminder that even the most seemingly permanent features in our solar system are dynamic and evolving. By studying its slow decline, we are not just watching a storm shrink. We are learning fundamental lessons about fluid dynamics, weather patterns, and energy transfer on a scale that is simply impossible to replicate. The fate of this giant storm is tied to the deepest mysteries of Jupiter itself, a planet that is both a protector whose gravity shepherds asteroids and a laboratory showing us the awesome power of planetary atmospheres. After exploring the crushing density of neutron stars and the slow fade of Jupiter's great storm, let's turn our attention to worlds that sound like they were dreamed up in a science fiction novel. Imagine an entire planet where the ground beneath your feet isn't rock or ice, but a glittering, endless crust of diamond. This isn't just a fantastical idea. It's a very real theoretical possibility supported by our understanding of planetary science, and we may have already found candidates orbiting distant stars. The existence of such diamond planets hinges on one crucial element: carbon. Our own Earth is a silicon-based world, rich in oxygen and silicate rocks. But around other stars, especially those that formed from clouds rich in carbon, the story can be completely different. In these carbon-rich systems, the material that coalesces into planets would be dominated by carbon compounds rather than the rock-forming silicates we're familiar with. The recipe for a diamond world begins with one of these carbon-rich protoplanets forming much closer to its star than Earth is to the Sun. This proximity creates scorching surface temperatures, but the true transformation happens deep within. As the planet cools and solidifies under its own immense gravity, the internal pressure becomes so astronomical that it forces the carbon atoms into a tightly packed crystalline structure. This is the exact same process that creates diamonds deep within the Earth, but on a planetary scale. Instead of a gemstone measuring a few centimeters, you get a mantle and crust that could be thousands of miles thick, made almost entirely of diamond. The most famous candidate for such a world is an exoplanet known as 55 Cancri E, located about 40 light-years away in the constellation Cancer. This planet is classified as a super-Earth, a world with a radius about twice that of our own and a mass nearly 8 times greater. It orbits its sun-like star so closely that a single year passes in just 18 hours, and the daytime temperatures are hot enough to melt iron. Initial studies of its parent star revealed a much higher carbon-to-oxygen ratio than our Sun, providing the perfect raw ingredient for a carbon planet. While later observations have suggested it might be less glamorous, perhaps a lava world with a thick atmosphere. The initial hypothesis sparked the imagination and demonstrated the potential for such exotic worlds to exist. The conditions on a diamond planet would be as hostile as they are dazzling. A landscape of diamond would be incredibly hard and brittle, likely forming sharp, jagged mountain ranges unlike any geological feature on Earth. With no water or silicate rocks to facilitate plate tectonics, the planet would be geologically dead, its surface unchanging for eons. The intense gravity of a super-Earth would make even standing up a Herculean effort, and the searing heat from the nearby star would create a surface of unimaginable extremes. These worlds remind us that the universe is a place of infinite variety, where the same basic laws of physics and chemistry can combine in profoundly different ways to create environments that defy our earthly expectations. The search for diamond planets continues, pushing our detection methods to their limits as we sift through the light of distant stars for the telltale glint of a truly precious world. If you thought the slow fade of Jupiter's great red spot or the impossible density of a neutron star were strange, then prepare for one of the most enduring and counterintuitive mysteries in our very own solar system. It involves a paradox so baffling that even the most brilliant physicists have struggled for decades to find a complete answer. We're talking about the Sun, the very heart of our planetary system, and a simple yet profound question: why is its atmosphere hundreds of times hotter than its surface? Logic would suggest that as you move away from a heat source, the temperature drops. If you stand near a campfire, you feel the heat. As you step back, it gets cooler. The Sun, however, completely defies this common-sense expectation. The Sun's visible surface, the photosphere, is what we see as its bright disk. It has a temperature of around 5,500 degrees Celsius, hot enough to vaporize any known material. But if you travel upward from this searing surface into the Sun's outer atmosphere, a wispy, shimmering halo called the corona that becomes visible during a total solar eclipse, the temperature doesn't fall. It skyrockets. The corona routinely reaches temperatures between 1 and 2 million degrees Celsius, and in some regions it can even soar to tens of millions of degrees. It's as if you walked away from a blazing fire and a few feet away found yourself surrounded by flames that were suddenly 1,000 times hotter. This is the coronal heating problem, and solving it requires us to look beyond simple thermal conduction and into the realm of complex magnetic phenomena. The key to the mystery lies in the Sun's magnetic field, an invisible, dynamic web of force that is generated by the churning, electrically charged plasma in the Sun's interior. This magnetic field doesn't just sit there. It's constantly being twisted, tangled, and stretched by the Sun's rotation and the convective motion of its gases, like a pot of vigorously boiling water. This constant motion stores enormous amounts of energy in the magnetic field lines, which arc up from the Sun's surface and loop through the corona. Scientists have two leading theories for how this stored magnetic energy is then released as heat, and it's likely that both processes are at work. The first theory involves magnetic waves. As the magnetic field lines are jostled and shaken at the Sun's surface, they can generate powerful waves that travel upward, much like shaking one end of a rope sends waves traveling along its length. These are called Alfvén waves. As these waves travel into the much thinner plasma of the corona, they gain energy and eventually crash like ocean waves breaking on a shore. This breaking or dissipating process converts the wave's energy directly into heat, supercharging the coronal gas. Think of it as the Sun's atmosphere being continuously heated by a constant, invisible earthquake shaking energy into it from below. The second major theory points to a phenomenon known as nanoflares. The Sun is known for its massive, dramatic solar flares, explosive events that can release the energy of millions of hydrogen bombs. Nanoflares are proposed to be the tiny, ubiquitous cousins of these giant flares. They are thought to be caused by a process called magnetic reconnection. When tangled magnetic field lines are stretched too far, they can suddenly snap and reconfigure themselves into a more stable arrangement. This sudden reconnection releases a tremendous burst of energy, accelerating particles and heating the surrounding plasma. While an individual nanoflare is incredibly small, a billionth the power of a large solar flare, the theory suggests they are happening everywhere all the time, in a constant, sparkling rain of miniature explosions. If there are enough of them, this relentless drizzle of energy could be more than enough to account for the corona's staggering temperature. This isn't just an academic puzzle. Understanding the corona is crucial for our own technological society. The superheated corona is the source of the solar wind, a constant stream of charged particles that flows outward through the solar system. When this wind interacts with Earth's magnetic field, it can create the beautiful auroras, but during periods of intense solar activity, it can also trigger violent geomagnetic storms. These storms have the potential to disrupt satellites, knock out power grids, and disrupt global communications. By unraveling the secret of why the corona is so hot, we are also learning to predict the sun's behavior, helping to safeguard the technological infrastructure that modern life depends on. So the next time you feel the sun's warmth on your skin, remember that you are experiencing just a fraction of its story. The true furnace lies not in the brilliant surface, but in the invisible million-degree crown that surrounds it, a testament to the hidden and powerful forces of magnetism that rule our star. Now, if you think a diamond planet sounds like an unlikely place to find something familiar, our next stop will really turn your assumptions about the solar system upside down. Let's travel to Mercury, the swift-footed messenger of the gods and the planet closest to the sun. The images we have of this world show a barren, cratered landscape baked by solar radiation, where daytime temperatures can soar to a scorching 430 degrees Celsius, hot enough to melt lead. It seems like the last place in the entire solar system you would ever find a single molecule of water. But the universe is a master of paradox, and Mercury holds one of the best. Hidden away at its poles in the permanent, deep freeze shadows of certain craters lies a significant amount of water ice. How can a planet that is practically in the furnace of the sun harbor frozen water? The answer lies not in its proximity to the sun, but in its unique and almost non-existent axial tilt. Unlike Earth, which is tilted on its axis by about 23.5 degrees, giving us our seasons, Mercury is tilted less than 1 degree. This means its rotational pole is almost perfectly perpendicular to its orbit around the sun. Because of this, the sunken floors of craters located at the north and south poles never, ever see direct sunlight. They are cast into an eternal, profound darkness, a permanent night that has lasted for billions of years. Without any atmosphere to speak of to transport heat around the planet, the temperature in these shadowed abysses can plummet to a bone-chilling negative 170 degrees Celsius. In this deep cold, water ice becomes as stable as rock, able to persist for eons just a stone's throw from the inferno of the sunlit surface. The first clues to this bizarre reality came not from visual images but from radar. In the early 1990s, astronomers using powerful radio telescopes on Earth, like the Arecibo Observatory, beamed radar signals toward Mercury. When the signals bounced back, they revealed something astonishing. Certain spots near the poles were reflecting the radar waves with a signature that was bright and highly polarized, a pattern characteristic of clean water ice. It was a stunning revelation, suggesting that frozen reservoirs were hiding in plain sight. But it was NASA's a messenger mission, which orbited Mercury from 2011 to 2015, that provided the definitive proof and transformed this radar ghost into a confirmed reality. Messenger carried a suite of instruments designed to probe these shadowy regions. Its neutron spectrometer detected a telltale signature of hydrogen, the key component of water ice, concentrated exactly in the permanently shadowed craters that the radar had flagged. Furthermore, by carefully mapping the topography and illumination of the poles, The spacecraft's laser altimeter could pinpoint which crater floors were in perpetual darkness. The correlation was perfect. The highest concentrations of hydrogen were found in the coldest, darkest places. Some of this ice is even exposed right at the surface, covered by only a thin layer of dark, insulating dust. But where did this ice come from in the first place? A planet so close to the Sun certainly didn't form with vast oceans that later froze. The leading theory is that the water was delivered to Mercury, just as it was to Earth and the Moon, by a constant rain of comets and water-rich asteroids over billions of years. When these objects impact Mercury, the tremendous heat of the collision would vaporize most of their water, sending it out into space or across the planet's surface. But any water molecules that happen to randomly bounce or migrate into the polar cold traps would instantly freeze and become permanently sequestered. It's a cosmic sorting process where the violent chaos of impacts ultimately delivers water to the only places in the entire Mercurian environment where it can survive. This discovery does more than just add a curious fact to a planetary profile. It fundamentally changes our understanding of how water, the essential ingredient for life as we know it, is distributed throughout the solar system. It shows that a world doesn't need to be in the habitable zone to possess water. What matters is the local environment, the presence of these permanent cold traps. This principle applies not just to Mercury, but to our own moon, to the dwarf planet Ceres, and even to asteroids. It means that these shadowed craters are natural deep-freeze laboratories, preserving a pristine record of the water that has been bombarding the inner solar system for eons. By studying Mercury's ice, we are effectively reading a history book of our solar system's early water delivery system, a book whose pages are written in frozen water and stored in the most unexpected of libraries. And now, let's return to that hellish world we visited earlier, Venus, because its strange atmospheric superrotation is only half of its story. The planet itself is spinning in a way that seems to defy common sense. We are taught that a day is the time it takes for a planet to spin once on its axis, and a year is the time it takes to orbit the Sun. On Earth, that works out neatly: 365 days in a year and 1 day every 24 hours. But Venus plays by a completely different set of rules. It takes Venus 243 of our Earth days to complete a single, slow rotation. Meanwhile, its journey around the Sun is considerably quicker, taking only 225 Earth days. This creates the mind-bending reality that a day on Venus is actually longer than a year on Venus. To make things even stranger, Venus spins in the opposite direction of almost every other planet in our solar system, a motion known as retrograde rotation. From a hypothetical vantage point high above the Sun's north pole, you would see most planets, including Earth, spinning counterclockwise. Venus, however, spins clockwise. This means if you could stand on its scorching surface, you would witness the Sun rising in the west and setting in the east, a cosmic spectacle found nowhere else in our immediate neighborhood. So how did Venus end up with this topsy-turvy, leisurely spin? Astronomers don't have a single, definitive answer, but the leading theory points to a traumatic past involving a colossal gravitational tug-of-war. One compelling idea is that Venus's thick, incredibly dense atmosphere played a crucial role. Over billions of years, the gravitational pull of the Sun on the planet's massive, soupy atmosphere may have created significant tidal forces. These forces, interacting with the planet's own rotation, could have acted as a brake, gradually slowing its spin down to the crawl we see today. This process, known as atmospheric tidal friction, is a bit like dragging your hand through water. The resistance slowly saps the energy of motion. Another, more dramatic hypothesis suggests that Venus suffered a giant impact early in the solar system's history, similar to the one that formed our moon. A collision with a protoplanet-sized object could have delivered such a powerful blow that it literally sent the planet spinning backwards, or stopped its rotation entirely, with the buildup of atmospheric tides later slowing it even further to its current snail's pace. It's also possible that Venus experienced a combination of these events, or that its spin was influenced by the gravitational perturbations of other planets over eons. The result is a world where time itself feels alien. A single solar day on Venus, the time from one sunrise to the next, is quite different from its sidereal day or rotation period because the planet is also moving along its orbit. Due to its retrograde motion, the time between sunrises on Venus works out to be about 117 Earth days. So, while the planet itself takes 243 days to spin, you would experience a sunrise roughly every 117 days. This creates a truly bizarre calendar. A Venusian year contains approximately 1.92 Venusian solar days. Imagine living in a place where you celebrate nearly 2 birthdays for every single trip you take around your star. This strange rotational dynamic is more than just a curious fact. It profoundly affects the planet's environment and climate. The extremely slow rotation means that each hemisphere is baked in continuous sunlight for months on end, contributing to the planet's runaway greenhouse effect and its uniformly scorching surface temperature. It also means that Venus has no protective global magnetic field like Earth, because our field is generated by the churning motion of conductive material in our planet's rapidly spinning core. Venus's sluggish spin isn't enough to power such a dynamo, leaving its surface exposed to the full onslaught of the solar wind. This unique combination of a long day and a short year stands as a powerful reminder that the planets in our solar system have lived violent and varied histories, and that the simple rhythms we take for granted on Earth are anything but universal. But for all its visual spectacle, space has long been portrayed as the ultimate silent movie, a vast, empty void where no one can hear you scream. It's a compelling and terrifying idea, this absolute silence. But here's the astonishing truth that shatters that common myth. Space is not silent. It's a cosmic concert hall, but we simply haven't been equipped to hear the music. The reason we think of space as silent is based on a fundamental physical truth. Sound, as we experience it, requires a medium to travel through. On Earth, that medium is our atmosphere. When something vibrates like a guitar string or your vocal cords, it pushes and pulls on the air molecules around it, creating a pressure wave that travels to your ear. In the near-perfect vacuum of space, there simply aren't enough atoms bumping into each other to carry those pressure waves. So, if you were floating in the void between stars, you would not hear the roar of a passing starship or the explosion of a supernova. That part of the myth is absolutely true. However, to say space is silent because there's no air is like saying the radio is silent because there's no music physically coming out of the box. It completely misses the invisible symphony happening all around us, a symphony written not in sound waves, but in electromagnetic radiation. Space is teeming with radio waves, plasma waves, and magnetic oscillations, and with the right technology, we can translate these vibrations into sounds that our ears can understand. This process is known as day-to-sonification, and it has given us a powerful new sense with which to explore the cosmos. One of the most haunting examples comes from our own planetary neighborhood. The Cassini spacecraft, during its epic mission at Saturn, had instruments designed to measure plasma waves in the planet's magnetic field. These aren't sound waves, but rhythmic vibrations in the charged gas or plasma that surrounds the ringed giant. When scientists converted these plasma wave measurements into audio frequencies, they discovered something beautiful and eerie. Saturn emits a slow, pulsing, ethereal chorus that sounds like something from a science fiction soundtrack. It's a complex signal that rises and falls, created by the interaction of the solar wind with Saturn's powerful magnetic field and the motion of its moons. It doesn't sound like a whistle or a simple tone. It has a choral, almost ghostly quality, as if the planet itself is singing a low, mournful song into the void. This isn't a sound you could hear with your own ears even if you were there, but it is a very real vibration of the space environment around Saturn, a direct recording of the planet's magnetic heartbeat. For something even more rhythmic and precise, we can listen to the dead stars we discussed earlier, pulsars. These rapidly spinning neutron stars emit powerful beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a cosmic lighthouse. If one of those beams happens to cross Earth's path, our radio telescopes detect a perfectly timed pulse. When these radio pulses are converted into sound, each pulsar has its own unique signature. Some sound like a steady, rapid-fire metronome, ticking with a regularity that rivals atomic clocks. Others have a deeper, more resonant thump, like a giant cosmic drum. The first pulsar discovered, known as CP1919, was so regular that the astronomers who found it jokingly nicknamed it LGM for Little Green Men, briefly entertaining the possibility it was an artificial beacon from an alien civilization. The sound of a pulsar is the sound of ultimate cosmic order, the relentless tick of a clock that has been running for millions of years, born from the chaotic death of a massive star. It is the universe keeping time on a scale we can barely comprehend. Perhaps the most profound sound we can extract from space, however, is the oldest one of all, the echo of creation itself. This is the sound of the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This radiation is a snapshot of the universe when it was just 380,000 years old, a time when it cooled enough for the first atoms to form and light could finally travel freely. It is the foundational static of our reality. When scientists sonified the data from spacecraft like NASA, a Wilkinson Microwave Anisotropy Probe, or WMAP, they weren't just creating a random noise. They were mapping the tiny temperature fluctuations in this ancient light, the slightly hotter and colder spots that would eventually seed the formation of galaxies and galaxy clusters. The resulting sound is a deep, resonant, and somewhat unsettling drone. It's a bass note of unimaginably low frequency, the sound of the entire universe ringing like a bell. Listening to it is like hearing the first vibration of existence, the fundamental tone that was struck at the moment of our cosmic origin. It is the closest we will ever come to hearing the birth of everything. So, while the classic line from the movie Alien is technically correct that in space no one can hear you scream, it omits a far more wondrous reality. Space is filled with a cacophony of vibrations, from the singing planets and the ticking pulsars to the deep hum of the Big Bang. We just needed to build the right instruments to act as our cosmic hearing aids, translating the silent songs of the universe into a symphony we can finally appreciate. After exploring the paradoxical ice of Mercury and the backward spin of Venus, our journey takes us to a world where the very concept of weather is redefined in the most brutal way imaginable. Located 64 light-years away in the constellation Vulpecula, the exoplanet known as HD 189733b presents a vision of hell that is both vivid and scientifically precise. This planet belongs to a class known as hot Jupiters, gas giants that orbit staggeringly close to their parent stars. In this case, the planet is locked in a gravitational embrace so tight that a single year lasts just 2.2 Earth days. This proximity creates an environment of almost incomprehensible extremes, where the distinction between atmosphere and surface blurs into a single, seething cauldron of violence. The most defining feature of this world, and the reason it captures the imagination of astronomers, is its weather, a perpetual global storm where the sky rains shards of glass sideways at supersonic speeds. To understand how such a phenomenon is possible, we need to look at the components of its atmosphere. Data from the Hubble Space Telescope has been instrumental in analyzing the light that filters through the planet's gaseous envelope during its transits across the face of its star. This analysis revealed a surprising and telling signature: the presence of silicate particles. Silicates are the dusty, grainy building blocks of rock common in the universe, but on HD 189,733b, they exist in a state of constant, violent flux. The daytime temperature on this world soars to a terrifying 900 degrees Celsius, hot enough to vaporize rock. Just as water evaporates from our oceans here on Earth, the immense heat on the day side of this planet literally boils the silicate-rich dust and rock in its atmosphere, turning it into a vapor of microscopic particles. This is where the exotic precipitation begins. These vaporized silicates are carried aloft by the planet's ferocious winds, and as they flow toward the marginally cooler night side, they have an opportunity to condense. In a process analogous to water vapor in Earth's atmosphere forming water droplets, the silicate vapor cools and coalesces, not into raindrops but into tiny particles of solid, molten glass. This is not a gentle drizzle. The weather system on HD 189,733b is driven by one of the most extreme temperature differentials in the known galaxy. Because the planet is tidally locked, meaning one hemisphere permanently faces the star while the other is locked in eternal night, the difference in heat between the day side and night side is colossal. This creates a titanic pressure gradient, much more powerful than any hurricane on Earth, which in turn fuels winds that race across the planet at speeds of up to 5,400 miles per hour. That is more than 7 times the speed of sound. These winds don't just blow, they scream across the planet's surface, scouring everything in their path. The newly formed glass particles are caught in this supersonic torrent, creating a relentless, horizontal hail of razor-sharp projectiles. Imagine standing in a storm where, instead of water, the air is thick with billions of tiny, superheated glass shards, all flying parallel to the ground with the force of a cosmic sandblaster. It's a storm that would effortlessly strip the flesh from bone and etch away solid metal in moments. The visual impression of this world, as interpreted by artists using scientific data, is as beautiful as it is terrifying. From a distance, the planet would appear as a deep, shimmering cobalt blue, a color not from oceans, but likely caused by the preferential scattering of blue light by the high-altitude silicate particles in its atmosphere, a permanent, global version of the haze that colors our own skies. But this serene, aquatic hue is a lie, masking the chaotic violence within. If you were to descend through its atmosphere, the sky would likely glow with an eerie, heated light filled with a mist of molten glass. There would be no solid surface to land on, only a deepening, burning haze of hydrogen and helium that transitions into an ocean of supercritical fluid deep within the planet's interior, a state of matter that is neither liquid nor gas. The entire experience would be one of being trapped in a vast, blue, incandescent furnace, endlessly buffeted by a hurricane of glass. The discovery and detailed study of HD 189,733b does more than just satisfy our curiosity about bizarre worlds. It serves as a crucial benchmark in exoplanet science. It was one of the first exoplanets where astronomers were able to directly detect and map the composition of its atmosphere, proving that we can characterize the conditions on worlds trillions of miles away. This hellish glass blower's furnace of a planet stands as a powerful testament to the sheer diversity of planetary systems, showing us that the universe is capable of crafting environments far beyond the limits of our own imagination, where the familiar processes of evaporation and condensation create weather from the stuff of rock and fire. But while we are contemplating worlds of unimaginable violence and alien weather, there is a place of profound silence and stillness much closer to home, a museum where the past is preserved in perfect, dusty detail. On the surface of our moon, the footprints left by the 12 Apollo astronauts, along with the tread marks of their lunar rovers and the discarded descent stages of their landers, are not just historical relics, they are permanent fixtures. Unlike on Earth, where wind, rain, and the relentless process of erosion would have long since scoured these marks away, the lunar landscape has kept them perfectly intact for over half a century, and it will continue to preserve them for millions of years to come. The reason for this incredible permanence boils down to the Moon being an almost perfectly static environment, devoid of the forces that constantly reshape our own world. The primary agent of destruction missing from the Moon is an atmosphere. Earth's blanket of air is a powerful, if gentle, sculptor. The wind, even a light breeze, carries tiny dust particles that act like a constant, slow-moving sandblaster, smoothing and weathering rock faces over time. Rainfall and flowing water are the most dramatic forces of erosion, carving canyons and washing away loose soil. The Moon has none of this. It exists in the hard vacuum of space, a place with no air, no wind, and no precipitation. A footprint left in the fine lunar soil, called regolith, experiences no weather. There is no gentle breeze to sift dust back into the impression, no raindrop to distort its sharp edges. The particles of regolith are jagged and unworn because there is no friction from an atmosphere to smooth them down. So when they are compressed by a boot, they lock together in a crisp, detailed mold that has no natural mechanism to be disturbed. Beyond the lack of air and water, the Moon also lacks significant geological activity. While the Moon is not entirely geologically dead, there is evidence of very subtle seismic tremors or moonquakes. It has no active plate tectonics, no volcanoes, and no processes that recycle its surface. On Earth, the movement of continental plates, volcanic eruptions, and the uplift of new mountain ranges ensures that no landscape is truly permanent. The entire surface of our planet is recycled over hundreds of millions of years. The Moon's crust, however, is a single, solid, and largely rigid shell. This means the same patch of ground in the Sea of Tranquility where Neil Armstrong took his one small step has remained fundamentally unchanged for billions of years, aside from the occasional new impact crater. The only force that actively reshapes the lunar surface is the random bombardment of micrometeorites. These tiny specks of space dust, some no larger than a grain of sand, strike the Moon at tremendous speeds because there is no atmosphere to burn them up. Over an immensely long timescale, millions upon millions of years, this constant microscopic pitting will very, very slowly mix the top layer of the soil in a process known as gardening. But this is an achingly slow and gentle process. It would take an estimated 10 to 100 million years to churn up just the top couple of millimeters of the lunar surface. A footprint several centimeters deep is essentially a permanent feature on this timescale, its sharp edges only gradually being filled in with the tiniest amounts of dust kicked up by these microscopic impacts. This incredible preservation gives the Apollo landing sites a unique status in the solar system. They are not just archaeological sites, they are pristine time capsules. The American flags, though likely bleached white by 50 years of unfiltered ultraviolet radiation from the sun, still stand on their poles. The lunar rovers sit parked exactly where the astronauts left them, their delicate wire mesh wheels still holding the perfect shape of their final turn. Even the discarded bags of human waste and the science experiments are all exactly as they were arranged, a snapshot of human activity frozen in time. This permanence highlights a profound sense of both our achievement and our fragility. Our mark on the cosmos in this one specific place will outlast every mountain range on Earth, every Grand Canyon, and nearly every trace of human civilization on our own dynamic planet. Long after the pyramids have crumbled to sand and our great cities have been reclaimed by the forests, those silent, ghostly footprints will remain, a testament to the brief moment when humanity reached out from its cradle and left a permanent signature on another world. Just when you think you have a handle on the scale of cosmic time, the universe reveals a secret that recalibrates our entire understanding of our solar system's history. We often look at Saturn with its stunning and majestic rings as an ancient permanent feature, a symbol of the timeless beauty of the cosmos. But here is the astonishing truth: Saturn's rings are not primordial. They are cosmic newcomers. The magnificent icy halo we see today likely did not exist when the first dinosaurs walked the Earth, and instead may have formed while Tyrannosaurus rex was the apex predator, a mere 100 to 200 million years ago. This discovery fundamentally shifts our perspective, turning a seemingly eternal structure into a fleeting and perhaps temporary spectacle in the grand timeline of our solar system. The evidence for this youthful age comes not from looking at the rings themselves, but from listening to the subtle way they interact with their parent planet. This crucial data was delivered by the Cassini spacecraft during its final, daring maneuvers, a mission phase poetically named the Grand Finale. As Cassini repeatedly dove between the planet and its innermost rings, it acted as a precise gravitational sensor. Every object with mass exerts a gravitational pull, and the immense collection of ice and dust particles that make up the rings exerts its own tiny tug on a spacecraft. By meticulously tracking the slight changes in Cassini's velocity as it flew through this region, scientists could measure the total mass of the rings with unprecedented accuracy. The results were definitive. The rings are far too light to be 4.5 billion years old. Their total mass is roughly equivalent to that of Saturn's mid-sized moon, Mimas. This mass is the key to the mystery. A heavier, more massive ring system would have been better equipped to withstand a relentless process of pollution and darkening. Over billions of years, the pristine ice of the rings would have been steadily bombarded by micrometeoroids, dark, dusty debris that constantly drifts through the solar system. This constant rain would have gradually painted the rings a much darker, sootier color. The fact that the rings are still so brilliantly bright and reflective means they have not had enough time to accumulate a significant amount of this dark contamination. They are, in cosmic terms, fresh and clean, pointing to a recent birth. So, if the rings are young, how did they form so recently in a solar system that is otherwise middle-aged? The leading theory is as dramatic as it is plausible: a catastrophic moon breakup. Saturn is a miniature solar system in its own right, with over 80 known moons locked in a complex gravitational dance. The current theory suggests that one of Saturn's primordial moons, perhaps a large, icy body similar to Mimas or Enceladus, was pushed into an unstable orbit. This could have happened through a slow, gravitational resonance with other moons, a process that gradually torques an orbit until it becomes dangerously eccentric. Once the doomed moon's path brought it too close to Saturn, it would have crossed the Roche limit. This is the critical distance from a planet where the tidal gravitational forces pulling an object apart become stronger than the object's own gravity holding it together. Inside this limit, a moon cannot remain intact. The difference in gravity between the side of the moon facing Saturn and the side facing away is so severe that it stretches the object, pulling it apart. The moon would have been torn asunder in a single cataclysmic event, shredded into a vast cloud of icy fragments. Some of this debris would have crashed into Saturn, while the remainder found itself in stable orbits, where countless collisions ground the fragments down and spread them out into the flat, broad disk of countless particles we see today. The rings we admire are the glittering scar tissue from this violent, ancient collision, the remains of a lost moon that ventured too close to its giant parent. This revelation carries a profound and somewhat melancholic implication. We are living in a special era. Saturn's rings are not a permanent fixture. They are a dynamic and evolving structure, and current research suggests they may not last more than another 100 million years or so. The same particles that make up the rings are under constant assault. Some are being pulled down into Saturn's atmosphere by its gravity, while others are being pushed outward by the pressure of sunlight in a process known as a ring rain. Data from Cassini and other observatories confirms that this drainage is happening at a measurable rate. The rings are quite literally disappearing before our eyes, albeit on a timescale that dwarfs human history. This means that for most of the solar system's long history, Saturn appeared as a bland, ringless gas giant, and in the distant future it will likely return to that state. The fact that we, as a species, have evolved and developed the technology to see and appreciate this breathtaking ring system during its brief, brilliant prime is a staggering coincidence. It's a humbling reminder that the cosmos is not a static museum display, but a vibrant, ever-changing arena where grand events unfold on timescales beyond human comprehension. Yet we are uniquely positioned to witness one of its most spectacular, if temporary, performances. From the temporary rings of Saturn, we now journey to the very edge of the observable universe, to a discovery so vast it redefines the word ocean. Imagine collecting every drop of water from all of Earth's oceans, from the deepest trenches of the Pacific to the frigid currents of the Arctic. Now multiply that volume by 140 trillion. The result is the amount of water vapor suspended in a single, colossal cloud surrounding a powerful quasar 12 billion light-years away, making it the largest and most distant reservoir of water ever detected. To grasp this scale, consider that 1 trillion is a 1 followed by 12 zeros. 140 trillion is a number so large it becomes almost abstract. It represents more water than exists in our entire solar system, a floating aquatic universe in its own right. This isn't a placid lake in space. It's a tumultuous, heated halo of vapor enveloping a cosmic powerhouse, and its existence tells a revolutionary story about how common the ingredients for life are across the cosmos. This incredible find revolves around an object known as a quasar, short for quasi-stellar radio source. A quasar is not a star, but the intensely bright, active nucleus of a distant galaxy. At its heart lies a supermassive black hole, billions of times more massive than our Sun. As vast quantities of gas, dust, and even entire stars spiral into this gravitational abyss, the material doesn't just vanish quietly. It forms a searingly hot, spinning structure around the black hole called an accretion disk. The friction and gravitational forces within this disk heat the material to millions of degrees, causing it to glow with a brilliance that can outshine the entire galaxy that hosts it. It is within the more extended material swirling toward this cosmic engine that the water vapor was found. The specific quasar, named APM 08279+5255, is so far away that the light we see from it began its journey when the universe was only about 1.6 billion years old, a mere toddler in cosmic terms. The discovery, made using instruments like the Z-spec instrument at the Caltech Submillimeter Observatory and the Combined Array for Research in Millimeter Wave Astronomy, relied on detecting a unique spectral fingerprint. Water molecules, even in the cold of space, can rotate and vibrate in specific ways, and when they do, they emit or absorb light at very particular wavelengths. The scientists were looking for a signature related to water vapor in a state known as a maser, which is like a natural laser for microwave radiation. What they found was a signal of staggering strength, indicating an unimaginable concentration of water. The sheer volume of water in this single cloud challenges a previously held assumption that in the early universe water must have been relatively scarce. The elements essential for water, hydrogen and oxygen, had to be forged first. Hydrogen has existed since the Big Bang, but oxygen is a product of stellar nucleosynthesis. It is created in the nuclear furnaces of stars and scattered throughout space when those stars die in supernova explosions. For a cloud of this magnitude to have formed only 1.6 billion years after the universe began, the process of element creation and distribution must have been incredibly rapid and efficient. This quasar's environment provides the perfect factory. The powerful radiation from the accretion disk is constantly tearing molecules apart, but in the cooler, denser regions of the surrounding gas and dust, thousands of light years across, these atoms can recombine. Here, oxygen atoms readily bond with the abundant hydrogen, forming water molecules on the surfaces of interstellar dust grains. The intense energy from the quasar then shakes these molecules loose, creating the massive envelope of vapor that we detect. This tells us that the universe, even in its youth, was already a prolific chemist, capable of manufacturing life's most crucial ingredient on a scale that dwarfs our wildest imaginations. The implications of this discovery ripple outward, touching on one of the most profound questions we can ask. Are we alone? Water is the universal solvent, the medium in which the complex chemistry of life as we know it occurs. Finding it in such unbelievable abundance and so early in cosmic history strongly suggests that the basic conditions for life are not rare or special to our little corner of the galaxy. They are a common, even inevitable, outcome of the physics of star formation and galaxy evolution. Wherever you have a sufficiently energetic environment to forge heavy elements and a cool, dense region for them to coalesce, you can form vast quantities of water. This means that when planetary systems began to form around the second and third generations of stars, they were likely already seeded with this vital resource. The water in your glass, the rain that falls from our sky, and the oceans that cover our world may have originated from processes just like those seen in this ancient quasar, a legacy of cosmic chemistry that links us directly to the earliest epochs of the universe. This vast reservoir is more than a record-breaking curiosity. It is a beacon illuminating the truth that water, and therefore the potential for life, is woven into the very fabric of the cosmos. From the ancient, watery halo of a distant quasar, we now travel to our planetary neighbor, a world that holds the record for one of the most extreme geological features anywhere. On the surface of Mars stands a volcano so colossal it redefines the very scale of planetary mountains. This is Olympus Mons, the undisputed king of volcanoes in our solar system, a shield volcano whose dimensions are so vast they are almost impossible to grasp. To stand at its base is to look up at a slope that rises so gradually it appears to be a mere gentle incline, yet it climbs to a breathtaking height of nearly 22 kilometers or about 13.7 miles. That is almost 2.5 times the height of Mount Everest above sea level, but its true immensity isn't just in its height, it's in its footprint. The base of Olympus Mons spans an area roughly the size of the entire state of Arizona, covering over 120,000 square miles. If you were to place it over the city of Phoenix, it would not only cover the city but the entire surrounding state, its caldera, the summit crater, stretching 50 miles across, large enough to swallow the island of Oahu whole. This isn't just a mountain, it's a geological continent unto itself. To truly appreciate the scale of Olympus Mons, we need to compare it to the giants we know on Earth. Our planet's largest volcano, Mauna Loa in Hawaii, is also a shield volcano built from countless fluid lava flows. From its base on the seafloor to its summit, Mauna Loa stands about 9 kilometers tall, making it taller than Mount Everest from base to peak. However, most of its mass is hidden beneath the ocean. In contrast, every staggering meter of Olympus Mons stands above the surrounding plains of Mars. Its volume is so immense that it contains about 100 times more material than Mauna Loa. If you could somehow transport Olympus Mons to Earth and set it down in the United States, its base would stretch from the outskirts of San Francisco to the edge of Los Angeles, and its summit would soar high above the cruising altitude of commercial jetliners. So how did Mars, a planet only half the diameter of Earth, manage to grow such an incomprehensible geological behemoth? The secret lies in a perfect storm of planetary conditions that no longer exist on our own world. The first and most critical factor is the absence of plate tectonics on Mars. On Earth, the crust is broken into a puzzle of shifting tectonic plates that slowly drift across the planet's surface. This movement creates a geological conveyor belt. A volcanic hotspot like the one that built the Hawaiian Islands stays fixed in place, burning through the Earth's mantle. As the Pacific Plate slowly moves northwestward over this hotspot, it creates a chain of volcanoes. The Big Island of Hawaii is the youngest and currently active volcano in this chain, but given enough time, it will move off the hotspot and become extinct while a new island begins to form to its southeast. This process limits the amount of lava any single volcano can accumulate. Mars, however, is a one-plate planet. Its crust is a single, solid, global shell. This means that when a mantle plume, a column of hot, buoyant rock, welled up beneath the surface of Mars billions of years ago, it stayed locked in one place. The volcano that formed above it, Olympus Mons, remained stationed over this prodigious source of magma for its entire multi-billion-year lifespan. Without any tectonic motion to carry it away, the lava simply kept pouring out, layer upon layer, flow upon flow, building a mountain to heights unimaginable on our dynamic Earth. The second crucial factor is Mars's lower surface gravity. At just 38% of Earth's gravity, the Martian crust can support much greater weights without sagging or fracturing. On Earth, the immense mass of a volcano the size of Olympus Mons would cause the entire tectonic plate to bend and subside under the load, effectively limiting its growth. On Mars, the crust could bear the phenomenal weight, allowing the volcano to push ever higher into the thin, cold air. The combination of a stationary crust and forgiving gravity created the perfect incubator for a geological superpower, a volcano that grew unchallenged for eons, becoming a permanent monument to the raw, untamed forces that once shaped the red planet. We've ventured to molten glass rain and diamond planets, but now let's uncover a type of star so cool that, if you could get close enough, you might not need a spacesuit to survive the temperature, just a very sturdy ladder. The universe contains a class of failed stars known as brown dwarfs, mysterious objects that blur the line between planet and star. These cosmic in-betweeners form just like stars from the collapse of a cloud of gas and dust, but they simply don't have enough mass to trigger the one process that defines a true star: sustained hydrogen fusion in their cores. Imagine an object dozens of times more massive than Jupiter, yet without the internal fire to truly shine. They are born with a warm glow from the heat of their formation, and then they slowly cool and fade over billions of years, destined to become cold, dark orbs drifting through the galaxy. The coolest category of these objects, known as Y-class brown dwarfs, are perhaps the most bizarre of all. Their surface temperatures can be as low as room temperature on Earth, somewhere around 20 or 25 degrees Celsius. That means, in theory, if you could stand on the cloud tops of one of these objects, though their immense gravity would crush you instantly, the ambient heat you'd feel could be no more threatening than the air in your own living room. These are stars you could literally touch if such a journey were possible. To understand why they're so cool, it's helpful to think of brown dwarfs as the universe's failed ambitions. A true star, like our Sun, is a continuous nuclear furnace. The immense pressure and temperature at its core, reaching millions of degrees, force hydrogen atoms to fuse into helium, releasing the colossal energy that makes stars bright. For this to happen, an object generally needs to be at least about 75 to 80 times the mass of Jupiter. Brown dwarfs fall short, ranging from about 13 times Jupiter's mass up to that stellar threshold. An object with 13 times Jupiter's mass is just heavy enough to briefly fuse a rare isotope of hydrogen called deuterium, and slightly heavier ones can fuse lithium for a short time, but these are fleeting fires. They burn through their deuterium fuel in a cosmic blink, perhaps only a few million years, and then the main nuclear show never starts. After that, they have no internal energy source to fight back against the relentless pull of gravity. They simply contract very slowly, radiating away their primordial heat into space, growing cooler and dimmer with each passing eon. They are, in essence, embers from a fire that never truly caught, cooling forever in the dark of space. The discovery of the Y spectral class was a triumph of infrared astronomy. Since these objects emit almost no visible light, they are invisible to optical telescopes. It took space-based observatories like NASA, a Wide-Field Infrared Survey Explorer, or WISE, to detect their faint thermal glow. One of the first and most famous examples is a brown dwarf named WISE 0855-0714, located just 7.2 light-years away. Its temperature is estimated to be between -48 and -13 degrees Celsius, colder than a winter day in Antarctica. While that's far too cold for a comfortable touch, it proved that brown dwarfs could indeed reach temperatures we experience on Earth. The even cooler, room temperature examples are the current frontier, the faintest and most difficult to detect. Finding them involves sifting through enormous amounts of infrared data, looking for the tiniest of warm specks against the cold background of space. Confirming their temperature requires analyzing their spectra, the unique fingerprint of light they emit, to look for the signatures of molecules like methane, water vapor, and even ammonia, compounds you would never find in the searing atmosphere of a true star, but which can form in the relatively balmy, planetary-like conditions on a wide dwarf surface. The existence of these touchable stars forces us to rethink our definitions. What exactly is the difference between a planet and a star? We used to think it was simple: planets orbit stars and stars shine by their own light. But brown dwarfs, especially the free-floating ones that drift alone through interstellar space, challenge that. They shine with their own dim, cooling light, yet they never achieve true stardom. Their atmospheric physics is a bizarre hybrid, more akin to a gas giant planet like Jupiter than to the Sun. They likely have complex cloud layers, not of water vapor, but of molten iron and silicate dust, with storms and jet streams that could dwarf anything in our own solar system. Some theoretical models even suggest that the very coolest brown dwarfs could have water clouds in their upper atmospheres. Picture that for a moment: a star-like object with water cloud weather patterns and a surface temperature where a human, protected from gravity and atmosphere, could theoretically survive the ambient heat. This strange reality makes brown dwarfs one of the most fascinating and poorly understood populations in our galaxy, a hidden kingdom of warm, dark giants that are only now beginning to step out of the shadows and into the light of our understanding. And after exploring the failed, cool fires of brown dwarfs, we come to a concept that applies to the entire cosmos. The universe itself has a temperature. It's a strange thought, isn't it? We're used to temperatures being a local phenomenon: the warmth of the sun, the cold of space, the climate of a planet. But astronomers have discovered that if you could take a thermometer and hold it in the deepest, emptiest void between galaxies, far from any star or planet, it wouldn't read absolute zero. Instead, it would register a faint, ubiquitous warmth of about 2.7 Kelvin. That is 270.45 degrees below 0 Celsius, a mere 2.7 degrees above the theoretical absolute zero where all molecular motion stops. This isn't just a theoretical number, it is a real, measurable heat that fills every cubic centimeter of the universe, a ghostly afterglow from the birth of everything, and it's known as the cosmic microwave background radiation. To understand this cosmic warmth, we have to rewind the clock all the way back to the very beginning, to a time when the universe was not cold and dark, but searingly hot and brilliantly bright. In the first moments after the Big Bang, the entire cosmos was an opaque, dense soup of energy and fundamental particles, a raging furnace so intense that light could not travel freely. Photons, the particles of light, were constantly being born and immediately absorbed or scattered by a thick plasma of electrons and protons. The universe was a blinding, chaotic fireball. This state persisted for about 380,000 years, a long time by human standards, but a mere blink in cosmic history. Then, a pivotal event occurred, one that astronomers call recombination. As the universe continued to expand, it also cooled. Eventually, it reached a temperature cool enough around 3000 Kelvin. for the frenetic electrons and protons to finally slow down enough to combine and form the first stable hydrogen atoms. This was a cosmic phase change of monumental importance. With the charged plasma suddenly neutralized into transparent gas, the photons that had been trapped in the cosmic fog were suddenly set free. In an instant, the universe went from opaque to transparent, and light could finally travel across vast distances for the first time. That first flash of liberated light is what we detect today as the cosmic microwave background. Imagine it as the ultimate baby picture of the universe, a snapshot of that exact moment of first light, now stretched and faded by 13.8 billion years of continuous cosmic expansion. This is where the microwave part of the name comes from. The original light was incredibly energetic, shining in the visible and ultraviolet parts of the spectrum. But as the fabric of space itself has stretched over billions of years, the wavelengths of that primordial light have been stretched along with it. Just as the sound of a siren drops in pitch as it moves away from you, a phenomenon called the Doppler effect, the light from the early universe has been redshifted from visible light all the way down into the much longer, lower energy microwave part of the spectrum. What was once a brilliant flash of optical light is now a faint, cool glow of microwaves bathing the entire cosmos. The most stunning evidence for this comes from the detailed maps we've made of this background. Satellites like NASA Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck mission have spent years scanning the entire sky to measure the tiny variations in this temperature. The resulting images are some of the most important in all of science. They show a remarkably uniform glow, a perfect thermal bath across the sky. But when you look closely, you see a mottled pattern, a cosmic tapestry of tiny hot and cold spots. These tiny fluctuations, variations of only about 100,000th of a degree, are the seeds of all future structure. They represent the slight over densities and under densities in the infant universe, places where gravity had just a little bit more to work with. Over billions of years, these microscopic ripples were amplified by gravity. The slightly denser patches pulled in more and more matter, eventually growing into the vast cosmic web we see today, the clusters of galaxies, the galaxies themselves, and the stars and planets within them. So, every time you look at one of those beautifully colored CMB maps, you are not just looking at a temperature chart of the sky. You are looking at the blueprint for our entire cosmic home, the genetic code from which everything we know, every star, every planet, and every one of us was ultimately formed. This discovery was so monumental that it earned the Nobel Prize in Physics because it provided the smoking gun evidence for the Big Bang Theory. Before its detection, there were competing ideas about the universe's origin, but the existence of this pervasive, cool background radiation was a prediction that only the Big Bang model could make. Finding it was a triumphant confirmation that our universe did, in fact, have a hot and dense beginning. The CBM is more than just a relic, it is a continuous presence. It is the oldest light that exists, and it is passing through your body as you watch this, a silent whisper from the dawn of time, reminding us that we are not just in the universe, but that the universe, in its most fundamental and ancient form, is all around us. After exploring the faint warmth that fills the void itself, we come to a comparison that has become almost a cliché in popular science, yet its truth is so staggering that it deserves to be unpacked and understood, not just repeated. You have likely heard it said that there are more stars in the universe than grains of sand on all the beaches and deserts of Earth. It sounds like an impossible exaggeration, a poetic flourish meant to convey a general sense of vastness. But the astonishing reality is that this statement isn't just a metaphor, it is a genuine and quite possibly conservative scientific estimate. To truly appreciate the scale of the cosmos, we need to move beyond the slogan and run the numbers, a process that reveals a universe of such profound immensity it can be difficult for the human mind to grasp. Let's begin with the sand. To estimate the number of grains, we first need to define our terms. We are considering all the sand on Earth, which includes the world's beaches, the vast deserts like the Sahara and the Arabian, and even the sand on the continental shelves beneath shallow seas. Now, how do we count them? We don't count them one by one, of course. We use volume and averages. First, geologists estimate the total volume of sand on the planet. This is a challenging figure, but a common estimate is around 7.5 times 10 to the 18th cubic meters. That is 7 quintillion, 500 quadrillion cubic meters of sand. Now, how many grains are in a single cubic meter? This depends on the size of the grain, but a fine-grained sand might have around 8 billion grains per cubic meter. If we multiply our total volume by that number of grains, we arrive at a truly colossal number. 7.5 times 10 to the 18th cubic meters multiplied by 8 billion grains per cubic meter gives us a figure of approximately 6 times 10 to the 27 grains of sand. That is a 6 followed by 27 zeros, 6 octillion grains. Now, let's look to the heavens. The number of stars is focused on the observable universe, the vast sphere of space from which light has had time to reach us since the Big Bang, a distance of about 46 billion light-years in every direction. Within this observable sphere, astronomers estimate there are roughly 2 trillion galaxies. That number alone is hard to fathom, but the real magic happens when we consider that these galaxies are not all identical. Our own Milky Way is a fairly average spiral galaxy containing an estimated 100 to 400 billion stars. If we take a conservative average of 100 billion stars per galaxy and multiply that by the 2 trillion galaxies, we get 200 billion trillion stars, which is written as 2 times 10 to the 23. However, this is now considered a low estimate. Many galaxies, particularly ancient elliptical galaxies, are far larger than the Milky Way, containing trillions of stars themselves. When we account for the full range of galaxy sizes, the estimated total number of stars in the observable universe balloons to a figure around 1 septillion. That is a 1 followed by 24 zeros, 10 to the 24, or 1,000 times a billion trillion. So, let's place these two inconceivable numbers side by side. We have roughly 6 times 10 to the 27 grains of sand on Earth, and approximately 1 times 10 to the 24 stars in the observable universe. At first glance, it seems the sand grains have it by a factor of about 6,000, but this is where a crucial nuance comes into play. Our stellar estimate is for the observable universe, the part we can see. The entire universe, beyond what our telescopes can detect, is almost certainly much, much larger and may very well be infinite. If the cosmos is infinite, then the number of stars is, by definition, infinitely larger than the finite number of sand grains on our single pale blue dot. Even if we confine ourselves to the observable realm, the comparison is humbling. A difference of a few thousand may seem large, but in the realm of exponents, these numbers are remarkably close. They inhabit the same order of magnitude, a fact that is, in itself, breathtaking. The countless grains of sand that have trickled through human hands for millennia, that form vast, impassable deserts and endless, shifting shorelines, are rivaled in number by the countless points of nuclear fire scattered across the cosmic ocean. This comparison does more than just stun us with a large number. It fundamentally reconfigures our perspective on our place in existence. Every one of those septillion stars is a sun. Many, likely most, are surrounded by planets. Our galaxy alone is now estimated to have more planets than stars. This means the universe is not a largely empty void punctuated by the occasional oasis. It is a teeming, vibrant metropolis of star systems, a cosmos that is practically overflowing with potential for worlds and perhaps life. When you stand on a beach and let the sand flow through your fingers, you are holding a tiny, tangible piece of a statistic that connects you directly to the grandest scale of all. Each grain is a reminder of the astronomical vastness that surrounds us, a whisper that the entirety of our world, for all its complexity and beauty, is but a single, insignificant speck in an ocean of suns. It is a perspective that is at once humbling and exhilarating, reminding us that the universe's capacity for creation is a force so powerful it can literally outnumber the very ground beneath our feet. While our minds tend to picture comets as silent, pristine, and beautiful icy wanderers, the reality of their composition is far less romantic and infinitely more pungent. Thanks to an incredible piece of interplanetary detective work, we now know that if you could get close enough to take a sniff of a comet's faint atmosphere, you would be greeted by an olfactory assault reminiscent of a combination of rotten eggs, horse stables, and a formaldehyde-rich chemistry lab. This bizarre sensory fact comes to us directly from the European Space Agency's Rosetta mission, which spent 2 years orbiting comet 67P, Churyumov-Gerasimenko, and used its onboard Rossina instrument, essentially a cosmic nose, to taste the gases steaming off the comet as it approached the Sun. As the comet's surface ices warmed, they sublimated, turning directly from solid to gas, and released a complex cocktail of molecules into the thin coma, or atmosphere, surrounding the nucleus. The Rossina instrument, a sophisticated mass spectrometer, was perfectly designed to identify and measure the abundance of these molecules. What it found was a veritable catalogue of stenches. The two most headline-grabbing culprits were hydrogen sulfide and ammonia. Hydrogen sulfide is the gas that gives rotting eggs their uniquely foul and unmistakable aroma, while ammonia is the sharp, acrid compound that forms the piercing scent of urine, particularly that of horses and other barnyard animals. But the unpleasant party didn't stop there. The scent profile was filled out by other acrid and toxic compounds. There was the intensely suffocating odor of hydrogen cyanide, the bitter almond scent famously associated with some poisons. Formaldehyde contributed its own piercing, preservative-like smell, and then there was methyl isocyanate and sulfur dioxide, adding their own sharp, irritating notes to the mix. The overall impression is not of a fresh, clean, icy world, but of a place that is profoundly alien and deeply unpleasant to the human nose. This discovery, while amusing, is far more than a simple cosmic curiosity. It provides a direct and powerful link back to the very beginning of our solar system. Comets like 67P are considered icy time capsules, leftover building blocks from the planet forming era 4.5 billion years ago that have been preserved in the deep freeze of the outer solar system. The specific mix of chemicals detected by Rosetta is a frozen recipe from that primordial kitchen. These molecules, hydrogen sulfide, ammonia, hydrogen cyanide, are all rich in the essential elements for life: carbon, hydrogen, nitrogen, oxygen, and sulfur. Astronomers often refer to these as prebiotic molecules, the raw ingredients that, under the right conditions, can react to form the amino acids and nucleobases that make up proteins and DNA. In fact, the same mission found the amino acid glycine, a fundamental building block of proteins, on the comet. This strongly supports the theory that comets could have been cosmic delivery trucks, ferrying these vital organic compounds to the early Earth during a period known as the Late Heavy Bombardment. The water in our oceans and the very chemistry that led to life may have arrived on these smelly, icy projectiles. So, the next time you catch a whiff of something foul, remember that the same stench that repels us today might have been the very scent of creation for our planet, the primordial aroma that seeded the world with the potential for life itself. From the stench of primordial comets to the faint echo of the Big Bang, we've explored how the universe engages our senses and challenges our perceptions of scale. But now we arrive at a concept that twists our understanding of reality itself, a phenomenon so fundamental that it governs the very flow of time. You might think of time as a constant, universal river, flowing at the same rate for everyone and everything everywhere. But this is an illusion. According to Einstein's theory of relativity, time is not absolute. It is malleable, a flexible fabric that can be stretched and warped by two things: motion and gravity. This effect is known as time dilation, and it means that time actually passes at different rates depending on where you are and how fast you are moving. Let's start with the effect of speed, known as special relativity. Imagine two identical twins. One twin stays on Earth, living a normal life. The other twin becomes an astronaut and embarks on a long journey on a spacecraft traveling at an incredible speed, a significant fraction of the speed of light. According to the theory, from the perspective of the twin on Earth, time on the fast-moving spaceship would appear to be flowing more slowly. Clocks on the ship would tick more slowly, and all processes, including the aging of the astronaut twin, would proceed at a reduced rate. When the traveling twin finally returns to Earth, they would be noticeably younger than their sibling who stayed behind. This isn't just a thought experiment. We see this play out on a tiny scale right in our own backyard. Astronauts living aboard the International Space Station are constantly in motion, orbiting the Earth at about 17,500 miles per hour. While that's incredibly fast by our standards, it's still only a tiny fraction of light speed. Yet the effect is measurable. Due to their velocity alone, astronauts on the space station experience time flowing slightly slower than we do on the surface. Over a typical 6-month mission, an astronaut will have aged about 0.005 seconds less than everyone on Earth. It's a minuscule amount, but it's real and confirms the predictions of Einstein's equations. But speed is only half the story. The other factor is gravity, described by general relativity. Einstein proposed that gravity is not a force in the traditional sense, but a curvature in the fabric of space-time caused by mass. A massive object like a planet creates a gravity well, and just as a ball would roll downhill into a valley, objects fall towards planets because they are following the curved geometry of space. This curvature also affects time. The deeper you are in a gravitational well, the stronger the gravity and the slower time passes. This means that your feet, being slightly closer to the Earth's center of mass than your head, actually age slower than your head, though the difference is so infinitesimally small it's impossible to measure. The effect becomes much more significant when we compare time on Earth to time in space. An astronaut on the space station is farther from Earth's center of mass than we are on the surface, so they are in a slightly weaker gravitational field. This effect counterintuitively causes time to run faster for them due to gravity, working in opposition to the slowing effect from their speed. For the space station's orbit, the gravitational effect is actually stronger than the velocity effect. The net result is that astronauts on the station age slightly faster than us on the ground, by about 0.003 seconds over a 6-month stay. So the two effects don't perfectly cancel out. The gravity effect wins, but only by a few thousandths of a second. The most powerful and everyday proof of this isn't found in space stations, but in the palm of your hand. The Global Positioning System, or GPS, would be completely useless if it did not account for both of these relativistic effects. Every GPS satellite contains an incredibly precise atomic clock. These satellites are orbiting about 12,500 miles above Earth, moving at high speed and in a much weaker gravitational field than clocks on the surface. If the software running the GPS system treated time as absolute, the calculations for your location would drift by several miles in just a single day. The engineers who designed the system had to pre-adjust the satellite clocks to compensate for these predicted time distortions. First, because the satellites are moving fast relative to us, their clocks run slower by about 7 millionths of a second per day due to special relativity. Second, because they are higher up in Earth's gravity well, their clocks run faster by about 45 millionths of a second per day due to general relativity. The net effect is that the satellite clocks tick faster than ground clocks by about 38 millionths of a second each day. This might sound negligible, but at the speed of light, that tiny time error translates to a positioning error of about 6 miles per day, which would accumulate rapidly, making turn-by-turn navigation impossible. So, every time you use your phone to find a coffee shop or navigate a new city, you are relying on Einstein's theory of relativity. Your device is constantly receiving time signals from satellites whose clocks have been intentionally skewed to account for the warping of space-time, providing a correction that makes modern technology work. This is not abstract physics. It is a practical engineering solution that confirms one of the most profound truths about our universe: that time itself is a relative experience shaped by our motion and our place in the gravitational cosmos. After contemplating the nature of time itself, we turn our gaze to the largest scales of the cosmos, where the universe reveals a structure so immense and so empty, it challenges our understanding of how matter is distributed. This isn't a brilliant supercluster of galaxies. It is a profound and staggering nothingness known as the Boötes Void, a region of space so vast and so barren it has been called the Great Nothing. Imagine a sphere in space so large that if you placed our entire Milky Way galaxy at its center, you would still have to travel through millions of light years of near-total emptiness in every direction before you even approached its edge. The Boötes Void is roughly 330 million light-years across. To grasp that scale, consider that our entire local group of galaxies, which includes Andromeda and dozens of smaller companions, is only about 10 million light-years wide. You could fit tens of thousands of galaxy groups like our own within the volume of this void and still have room to spare. When it was first discovered in the 1980s by astronomer Robert Kirshner and his team, it appeared to contain only a handful of galaxies, a density of matter so low it was unlike anything else seen in the cosmos. This discovery was made possible by the painstaking work of mapping the three-dimensional universe. Astronomers don't just take pictures of the sky, they measure the redshift of galaxies, how much their light is stretched by the expansion of the universe, to determine their distance. By plotting the locations of thousands of galaxies, they began to see the large-scale structure of the cosmos, a pattern often described as the cosmic web. This web is a magnificent, intricate architecture consisting of brilliant filaments and dense knots where thousands of galaxies cluster together, all separated by these vast, dark, and empty bubbles known as voids. The Boötes Void is the king of these bubbles, an overgrown void whose size seemed at first to defy the standard models of cosmology. In a universe that began with a nearly uniform distribution of matter after the Big Bang, how could gravity have left such an enormous region so completely empty? The initial surveys suggested only 60 galaxies were present in that colossal volume, a number so low it would mean the void was about 10,000 times emptier than the average density of the universe. This posed a serious problem. The tiny fluctuations in the cosmic microwave background, the blueprint for all structure, didn't seem to have ripples large enough to produce a void of this magnitude through gravitational collapse alone. It was as if someone had taken a giant cosmic cookie cutter and scooped out a sphere of the universe, leaving behind a baffling emptiness. The mystery of the Boötes Void has deepened and evolved with more advanced observations. Later, more sensitive surveys have revealed that the void is not quite as empty as it first appeared. Instead of 60 galaxies, we now know it contains perhaps 200 or more, though that is still a desperately small number for such an enormous volume. Most of these are small, faint dwarf galaxies huddled together in thin, thread-like structures that stretch across the emptiness like isolated islands in an ocean of darkness. This revised picture doesn't make the void any less mysterious, it simply reframes the question. The problem is no longer that the void is completely empty, but that it is so disproportionately large. The leading theories for its formation are as grand as the void itself. One compelling idea is that voids can merge just like galaxies. Smaller voids, which are common in the cosmic web, can grow over time as the universe expands. The gravitational evolution of the web can cause the walls between adjacent voids to thin and rupture, allowing them to coalesce into a single super-void. The Boötes void could be the product of many smaller voids merging together over billions of years, creating a single cavern of nothingness on a scale that is rare, but not impossible within our current cosmological models. Another, more speculative hypothesis involves the influence of something called dark energy, the mysterious force accelerating the universe's expansion. It's possible that dark energy acts more strongly in these underdense regions, giving them an extra push outward and causing them to expand faster than the rest of the universe, effectively inflating the void to its tremendous size. What would it be like to live inside such a place? If our solar system were located in the heart of the Boötes void, our night sky would be a profoundly different and lonely sight. Without the nearby glow of countless galaxies, the blackness between stars would be absolute. There would be no faint, fuzzy patch of the Andromeda galaxy to see with the naked eye, no Magellanic clouds, and no distant smudges of light from other galactic neighbors. The concept of a local group would be meaningless. The few stars in our own galaxy would be all we could see, with an endless, unbroken darkness stretching beyond. For astronomers in such a civilization, the discovery that the universe is filled with billions of other galaxies might have come much later, if at all, for their telescopes would have to peer across hundreds of millions of light years of emptiness before finding another island of stars. The existence of the Boötes void and others like it is a crucial piece of the cosmic puzzle. These vast, empty regions are not just curiosities, they are active players in the evolution of the universe. The relative emptiness inside a void creates a unique gravitational landscape. The pull of matter from the surrounding dense walls of the cosmic web actually exerts a tidal force on the void, causing galaxies within it to stream outward, away from the center of the emptiness and toward the denser regions. This void galaxy drift is a subtle but important effect that influences how structures move on the largest scales. The Boötes void, therefore, is not a static hole. It is a dynamic entity growing and evolving, its very emptiness exerting a gravitational influence on the fabric of the cosmos around it. It stands as a humbling monument to the fact that the universe is not just made of the things that glow, but is equally defined by the vast, silent, and majestic spaces in between. For generations, science fiction writers have dreamed of worlds with twin suns, most famously depicted in the unforgettable scene from Star Wars where Luke Skywalker gazes at a double sunset on his home planet of Tatooine. For a long time, this remained a beautiful piece of cinematic imagination, a fantasy that seemed too complex and unstable to exist in reality. But the universe, as it so often does, has surpassed our fiction. We now know that such planets are not only possible but are relatively common, and we have observed them directly. These are called circumbinary planets, worlds that orbit not one but two stars at the same time. The discovery of these systems has fundamentally altered our understanding of planetary formation, proving that it is robust enough to occur even in the chaotic gravitational environment of a binary star. The first confirmed discovery of a circumbinary planet, Kepler-16b, was a landmark moment in astronomy. Found by NASA, a Kepler space telescope in 2011, it orbits a pair of stars about 200 light-years away in the constellation Cygnus. The Kepler telescope used the transit method, detecting the tiny dip in starlight that occurs when a planet passes in front of its parent star. In a single star system, these dips are perfectly periodic. For Kepler-16b, the signal was far more complex. Astronomers observed dips in starlight from two different stars, and these dips were sometimes out of sync, revealing that the stars were eclipsing each other as they orbited, and that a third body, the planet, was transiting both of them. The stars in this system are a pair of relatively small, cool stars. The primary is a K-type star, about 69% the mass of our Sun, and its companion is an even smaller M-type star, a red dwarf with only 20% of the Sun's mass. These two stars whirl around each other in a tight, frantic dance, completing an orbit in just 41 days. The planet Kepler-16b is a gas giant with a mass similar to Saturn, and it orbits both stars at a distance of about 65 million miles. Its year is 229 Earth days, meaning it completes its journey around the binary pair in less time than it takes for Venus to orbit our Sun. This discovery shattered the assumption that the gravitational tug-of-war in a binary system would prevent planets from forming, proving instead that planets can coalesce in the disk of material that surrounds both stars. The orbital dynamics in a system like this are a fascinating celestial ballet, a delicate balance of gravitational forces. For a planet to have a stable orbit in a binary system, it must be located far enough away from the two stars that their gravitational pull is effectively merged into a single center of mass. This region is known as the circumbinary habitable zone. If a planet orbits too closely, the competing gravitational tugs from the two stars will disrupt its orbit, either sending it careening into one of the stars or ejecting it from the system entirely. The stable zone usually begins at about 3 to 5 times the separation distance between the two stars themselves. Inside this zone, the planet's path is not a simple, elegant ellipse like Earth's. Instead, its orbit wobbles over time. The gravitational push and pull from the two stars as they move around each other causes the planet's trajectory to oscillate, a phenomenon known as orbital precession. This means that the timing and duration of the planet's transits in front of the stars change measurably from one orbit to the next. For astronomers, this wobble is not a problem. It's a valuable clue that confirms the planet is indeed orbiting a binary pair and provides critical data about the masses of all the objects involved. For any potential life, or even just for a hypothetical visitor, the sky on a circumbinary planet would be a spectacle of constant change. The nature of the sunsets and the seasons would be unlike anything we experience on Earth. Because the two stars orbit each other so closely from the surface of Kepler-16b, they would appear as a single, elongated star for much of the day, only separating into distinct orbs when they were farthest apart in their mutual orbit. A sunset would be a breathtaking event. As the planet rotated, the two stars would dip below the horizon, but not necessarily at the same time. You might witness a double sunset, with one star disappearing followed by the other a short while later, casting complex, shifting shadows across the landscape. Conversely, you could have a double sunrise with the two stars peaking above the horizon in sequence. The seasons would be incredibly complex and unpredictable. On Earth, our seasons are dictated by the tilt of our axis as we orbit our single, steady sun. On a circumbinary planet, the seasons would be driven by a combination of 3 factors: the planet's axial tilt, its elliptical orbit around the binary center of mass, and the ever-changing positions and combined brightness of the two stars. As the planet travels along its wobbling path, the distance to the stellar duo changes, and the amount of energy it receives fluctuates. Furthermore, as the two stars eclipse each other every 41 days, there would be regular, brief dimming events. A noticeable drop in daylight and temperature, creating short, sharp eclipse seasons, superimposed upon the longer, more traditional seasonal cycles. The light itself would be strange, a blend of the different colors of the two stars, perhaps a mix of familiar yellow-white and a dimmer, redder hue, casting a permanent, alien tint over the world. Since the discovery of Kepler-16b, many more circumbinary planets have been found, each with its own unique characteristics. Some systems, like Kepler-34 and Kepler-35, feature planets orbiting two sun-like stars. Others push the boundaries of stability, like planets in the Kepler-47 system, which is home to at least 3 planets orbiting a pair of stars where one is similar to our Sun, and the other is a tiny red dwarf only 1/3 its size. Remarkably, one of these planets, Kepler-47c, orbits within the system's habitable zone, the region where temperatures could allow for liquid water. This raises the tantalizing possibility of a habitable world with two suns in its sky. The discovery of these Tatooine-like worlds has opened up an entirely new field of planetary science. It demonstrates that planet formation is an incredibly resilient process, capable of occurring in a much wider range of environments than we once thought. Nearly half of all Sun-like stars are in binary or multiple star systems, so the discovery of planets within them dramatically increases the number of potential real estate for planets in our galaxy. Each one is a natural laboratory for studying gravity and orbital mechanics, offering a window into the complex and beautiful dances that can occur under the influence of multiple suns. After exploring the stark emptiness of cosmic voids and the complex orbits of twin sun worlds, we venture now into a discovery that connects the grand scale of our galaxy to a sensation we can experience right here on Earth. It turns out that the center of our Milky Way has a flavor, and according to the chemical data, it tastes surprisingly like raspberries. This isn't science fiction or a whimsical analogy. It's a conclusion drawn from hard spectroscopic data that identified a specific molecule floating in a giant molecular cloud near the galactic core. The molecule is called ethyl formate, and it's a key contributor to the aroma of rum and, remarkably, the distinctive flavor of raspberries. Finding this single, complex organic compound in the void of interstellar space opens a window into the incredible chemical richness of our galaxy and forces us to reconsider the emptiness between the stars as anything but empty. To understand how we can possibly know what a distant cloud in space tastes like, we need to look at the incredible tool of spectroscopy. Every molecule in the universe has a unique fingerprint, not of its physical shape, but of the light it interacts with. When a molecule is energized, its atoms can vibrate and rotate in specific quantized ways. Each of these movements corresponds to the absorption or emission of light at a very precise wavelength. Think of it like a musical instrument. A violin and a trumpet playing the same note sound different because they produce a different set of overtones or harmonics. Similarly, a molecule like water and a molecule like ethyl formate, when energized, will interact with light in their own unique, complex patterns. Astronomers use powerful radio telescopes to observe the faint light coming from distant clouds of gas and dust. They don't see visible images of the molecules themselves. Instead, they see a spectrum, a graph of intensity versus wavelength. This graph looks like a messy line with many sharp dips and peaks. Each dip represents a specific wavelength of light that has been absorbed by the cloud. By matching the pattern of these dips or absorption lines against a library of known molecular fingerprints created in laboratories on Earth, scientists can say with confidence, that specific pattern of lines matches the signature of ethyl formate. It's a form of remote chemical analysis, allowing us to identify the ingredients in a cosmic recipe from 25,000 light-years away. The specific cloud where this delicious discovery was made is known as Sagittarius B2, the same colossal gas cloud we encountered earlier that contains vast quantities of alcohol. When researchers from the Max Planck Institute for Radio Astronomy were analyzing its spectrum, they found a forest of absorption lines, a clear sign of a rich and complex chemistry. Sifting through this data, they identified the unmistakable signature of ethyl formate. It's crucial to remember that the cloud itself isn't a giant, floating raspberry. The flavor we associate with the fruit is a complex combination of many different compounds working together. Ethyl formate is just one key player in that symphony of taste. So, while you wouldn't stick out your tongue and get a burst of fruity flavor if you could visit the cloud, its chemical blueprint contains one of the essential notes that creates that familiar sensation here on Earth. The significance of this goes far beyond a fun fact. The presence of such a large, complex organic molecule so far from any star or planet tells us something profound about the chemical capabilities of the universe. These molecular clouds are not just simple collections of hydrogen and helium, they are sophisticated chemical factories. The discovery of ethyl formate, along with amino acids and sugars found in other clouds and meteorites, demonstrates that the fundamental building blocks of life, and even the compounds that define our sensory experiences of food and drink, are being manufactured in the cold, dark depths of space long before they ever become part of a planet. This revelation ties directly into a concept known as astrochemistry, the study of the abundance and reactions of molecules in the universe. For a long time, scientists wondered if complex molecules could even survive the harsh radiation present in interstellar space. The fact that we find them in such abundance suggests that the surfaces of dust grains act as tiny cosmic laboratories. These microscopic particles provide a solid surface where single atoms and simple molecules can stick, meet, and gradually link up to form more complex structures, shielded from destructive radiation. Over millions of years, these grains can accumulate a mantle of icy, organic material. When a shock wave from a nearby supernova or the gentle warming of a forming star heats the cloud, these complex molecules can be released back into the gas where our telescopes can detect them. This process is thought to be a universal one, happening in molecular clouds throughout our galaxy and others. It means that every new star system is likely born from a cloud that has been pre-seasoned with a rich broth of organic molecules. The water in our oceans, the carbon in our bodies, and perhaps even the chemical precursors to the very senses that allow us to taste a raspberry, all have their origins in these vast, dark, and surprisingly flavorful nurseries between the stars. So, the next time you enjoy a handful of raspberries, consider the incredible journey of one of its key flavor compounds, a journey that began in a silent, rotating cloud of gas and dust near the bustling center of our Milky Way galaxy. Yet, even as we map the grand structure of the galaxy and the flavorful chemistry within its clouds, one of the most tantalizing astronomical mysteries remains much closer to home, hiding in the perpetual twilight of our own solar system's frontier. For decades, we've been taught that our planetary family is complete, a neat set of 8 worlds since Pluto's reclassification. But what if our census is wrong? A growing body of evidence, meticulously pieced together by astronomers, points to the gravitational fingerprint of a massive, unseen world, a hypothetical giant unofficially known as Planet 9. This isn't a direct observation, but a ghostly presence inferred from its influence, a cosmic detective story written in the bizarre, clustered paths of small, icy bodies far beyond Neptune. The clues to this mystery lie in the scattered disk, a region of the Kuiper belt populated by small, icy worlds on elongated and highly tilted orbits. While most of these objects have orbits that appear random, a team of researchers led by Caltech's Konstantin Batygin and Mike Brown noticed something strange. A specific group of these distant bodies, with orbits taking them hundreds of astronomical units from the Sun, share an odd commonality. Their points of closest approach to the Sun, their perihelia, are clustered together in space, and their orbital paths are tilted in a similar direction. Statistically, this kind of coordinated alignment is incredibly unlikely to happen by chance alone in the gravitational environment we currently understand. Imagine a dozen different clocks all set to ring at seemingly random times, yet you notice that a specific subset of them always chime within the same hour and their minute hands are all pointing in the same general direction. This peculiar clustering is the primary evidence for Planet 9. The most plausible explanation is that a massive, distant planet is herding these smaller objects through its immense gravitational pull, shepherding their orbits into this peculiar configuration over billions of years. Without such a shepherd, the gravitational nudges from the known giant planets should have randomized these orbits long ago. The persistent clustering suggests an unseen hand is actively maintaining this celestial order. So, what kind of world could this be, based on the gravitational influence required to sculpt these orbits? Planet 9 is hypothesized to be a substantial object, a true giant of the outer dark. Current models suggest it has a mass roughly 5 to 10 times that of Earth, which would make it a super-Earth or a mini-Neptune, a class of planet that is common around other stars but conspicuously absent from our own inner solar system. Its orbit would be equally colossal and alien. It's thought to follow a highly elliptical path, swinging from a closest approach of perhaps 200 astronomical units from the Sun, out to an almost unimaginable 600 to 1,000 astronomical units at its farthest point. To put that in perspective, at its most distant, Planet 9 would be over 20 times farther from the Sun than Neptune. A single year on this world would be staggeringly long, spanning 10,000 to 20,000 Earth years. Finding this needle in a cosmic haystack is the monumental task that now faces astronomers. The search is incredibly difficult because such a distant planet would reflect very little sunlight, making it exceptionally faint. It could be located anywhere along its multimillennial orbit, requiring surveys to scan vast areas of the sky for a single, slow-moving point of light. Major projects like using the Subaru telescope in Hawaii and analyzing data from the Dark Energy Survey are meticulously combing through the data. They are looking for that one faint dot that moves just a tiny amount against the backdrop of fixed stars over nights, weeks, or even years of observation. It's a painstaking process of elimination, ruling out known objects one by one in the hope of finding the one that doesn't belong. The potential discovery of Planet 9 would be far more than just adding a new world to our textbooks. It would be a revolutionary rewrite of our solar system's history and architecture. Its very existence raises a profound question. How did it get there? It's highly unlikely that a planet of such size could have formed so far from the Sun in the sparse protoplanetary disk of our youth. The leading theory is one of cosmic drama, a gravitational ejection. In the solar system's chaotic early days, the giant planets Jupiter, Saturn, Uranus, and Neptune are believed to have migrated from their original orbits. During this gravitational shuffle, it's possible that Planet 9 was formed much closer to the Sun, perhaps even between the orbits of the giants, before a close encounter with Jupiter or Saturn acted as a gravitational slingshot, hurling it out onto its vast, eccentric orbit. Instead of being ejected entirely from the solar system, its path was likely altered by the gravitational pull of passing stars in the Sun's birth cluster, trapping it in the distant outer darkness. If this theory is correct, Planet 9 is not an alien interloper but a long-lost sibling, a primordial giant that was exiled in a celestial game of gravitational pinball and has been silently circling our Sun ever since, its presence only betrayed by the subtle tug it exerts on the frozen debris at the edge of our knowledge. Its discovery would complete a chapter of our own origin story that we never knew was missing. We've explored silent movies in space, the hum of the Big Bang, and even the chemical taste of the galaxy, but stars themselves have a voice if you know how to listen. Far from being static points of light, stars are dynamic, vibrating spheres of plasma, and their surfaces are constantly rippling with waves, much like the skin of a drum. This field of study is known as astroseismology, and it allows us to peer deep into the hearts of stars by listening to the music they make. The principle is similar to how geologists use seismic waves from earthquakes to map Earth's interior. When an earthquake rumbles, it sends waves traveling through the planet, and by measuring how those waves speed up, slow down, or change direction, scientists can deduce the composition and structure of the layers deep below our feet. Astroseismology applies this same logic to the Sun and other stars. The constant churning and convective motion in a star's outer layers creates a cacophony of pressure waves that travel through its interior. Some of these waves bounce off the star's surface and reflect back inward, while others penetrate deep toward the core. As they travel, their behavior is exquisitely sensitive to the conditions they pass through, the temperature, density, and composition of the stellar material. By meticulously measuring the frequencies and amplitudes of these oscillations, astronomers can effectively perform a stellar ultrasound, constructing a detailed picture of the star's internal architecture that we could never see directly. The sounds we can create from this data are more than just a novelty. They are a direct translation of the star's physical vibrations. Our own sun is the most studied star in this regard, and its sound is a low, resonant, and constant hum. If space weren't a vacuum and sound could travel, the sun would not be silent. Instead, it would produce a deep, bass-like drone, the collective voice of millions of overlapping oscillation modes ringing out simultaneously. The pitch of this hum is determined by the star's size. A giant star with its vast, tenuous envelope vibrates slowly, producing a deep, low-frequency rumble. A small, dense white dwarf or a rapidly spinning neutron star, on the other hand, would oscillate at a much higher pitch. To make these vibrations audible to human ears, scientists take the actual frequency data collected by space telescopes and mathematically shift it upward into our audible range. The raw oscillations of a star like the Sun are far too low for us to hear. With periods of around 5 minutes, their fundamental frequency is about 3,000 cycles per second below the threshold of human hearing. By speeding up this data, sometimes by a factor of 40 or 50,000, we can hear the star's true voice transposed into a register we can perceive. The result for our Sun is a dense, chord-like sound, a meditative and somewhat haunting resonance that speaks to the immense, stable power at its core. The spacecraft that have made this possible are engineering marvels designed for this specific purpose. Missions like NASA's Kepler Space Telescope and the Convection, Rotation, and Planetary Transits, or CoRoT, mission, along with the more recent Transiting Exoplanet Survey Satellite, or TESS, were not just planet hunters, they were also stellar listeners. They observed thousands of stars for years, measuring their brightness with incredible precision. When a star pulsates, its surface moves inward and outward, causing its brightness to flicker ever so slightly. These flickers are incredibly subtle, often a change of just a few parts per million in the star's total light output. By analyzing these tiny, rhythmic changes in brightness over time, astronomers can tease out the individual frequencies of the star's oscillations, much like identifying the individual notes that make up a complex musical chord. This data is then transformed into a sound wave, where the frequency of the light oscillation becomes the frequency of the sound we hear. Listening to these stellar symphonies provides a wealth of scientific insight. Different oscillation modes probe different layers of the star. Some are sensitive to the surface, while others dive all the way to the core. By studying the mix of modes, scientists can determine a star's age, mass, and internal chemical composition with remarkable accuracy. For instance, the rate at which hydrogen is fused into helium in the core changes the star's internal structure over time, which in turn alters its resonant frequencies. This means we can effectively hear a star aging. We can also detect rapid internal rotation, magnetic fields, and even the presence of subsurface convection zones, all from millions of light years away, simply by tuning in to the star's unique song. Hearing the sound of a single star is fascinating, but the real power of astroseismology is revealed when we compare the songs of different stars. A young, massive star burns its fuel fiercely and has a different internal structure than an old, lower-mass star nearing the end of its life. This difference is reflected in their oscillations. A star in the red giant phase, for example, has a much deeper, slower, and more resonant hum than a star like our Sun, because its outer layers have expanded to an enormous size. The sound evokes the deep, mournful tone of a massive bell. In contrast, a smaller, hotter star might produce a brighter, more rapid series of pulses. These stellar sounds are not just abstract data points, they provide a direct, visceral connection to these distant suns. They transform them from silent points of light into dynamic, living entities with their own internal rhythms and life cycles. The next time you look up at the night sky, remember that it is filled with a silent, vibrating chorus. Each star is ringing like a bell, its unique song telling the story of its birth, its life, and its eventual fate. Through the science of astroseismology, we are no longer just stargazers. We have become listeners, able to decipher the hidden music of the cosmos and understand the inner workings of the universe's most fundamental engines. But as we listen to the resonant hum of the stars, we are surrounded by a far more elusive and ghostly presence, one that flows through you in unimaginable numbers as you watch this very video. Our universe is teeming with trillions upon trillions of what scientists call ghost particles, the neutrino. These are not particles in the familiar sense, like the protons and electrons that make up our world. They are ethereal wisps of matter, so intangible that they can pass through entire planets, and even you, as if nothing were there at all. To understand just how ghostly they are, consider this. Right now, trillions of neutrinos from the sun are passing through your body every single second, day and night, without a single one interacting with your atoms. They are the universe's most abundant particles with mass, and they are the ultimate cosmic messengers, carrying information from the most violent and secretive events in the cosmos, if only we can find a way to catch them. So, what exactly is a neutrino? Born from the heart of nuclear fires, a neutrino is a fundamental subatomic particle, a cousin to the electron, but with a set of properties that make it almost magical. They are electrically neutral, which means they are unaffected by the electromagnetic forces that govern most of the interactions in our daily lives. They have an almost incomprehensibly tiny mass. A neutrino is at least 10 million times lighter than an electron, which itself is a tiny fraction of the mass of a proton. But their most defining characteristic is their profound reluctance to interact with normal matter. The force that governs their rare interactions is the weak nuclear force, which, as its name implies, has an extremely short range and is, well, weak. For a neutrino to be stopped or deflected by an atom, it must score a direct, head-on collision with the atom's nucleus, a target so incredibly small compared to the vast emptiness within the atom itself that such an event is extraordinarily rare. To a neutrino, a light year of solid lead is barely an inconvenience. This is why they can stream directly from the core of the sun, travel 93 million miles through space, and then pass through the entire Earth as if it were a ghost. This incredible abundance starts with our own star. The sun's colossal energy output is generated by nuclear fusion at its core, where hydrogen nuclei are crushed together to form helium. In every single one of these reactions, two neutrinos are produced and immediately race outward at nearly the speed of light. Because they so rarely interact, they escape the sun's dense core in just over 2 seconds, whereas a photon of light can take tens of thousands of years to randomly bounce its way to the surface. The neutrinos hitting Earth right now are a direct, real-time snapshot of the nuclear fusion happening in the sun's core 8 minutes ago, but the sun is a mere trickle compared to the cosmic deluge. When a massive star explodes as a supernova, the collapse of its iron core is so violent and sudden that it releases a staggering pulse of neutrinos, carrying away 99% of the star's total energy in a burst that, for a few seconds, outshines the entire rest of the universe in neutrinos. During the famous supernova 1987A, which occurred in a neighboring galaxy, detectors on Earth recorded a total of 24 neutrinos over a 13-second span. That may not sound like much, but it was a landmark event confirming our theories about stellar death and marking the birth of neutrino astronomy. How do you possibly catch a ghost? You must build a trap of immense scale and patience, and you must hide it from the constant cacophony of other particles. This is why the world's most advanced neutrino detectors are engineering marvels located in some of the most isolated places on Earth, deep underground in working mines, beneath mountains, or at the bottom of the ocean. These locations use thousands of feet of solid rock as a natural shield to filter out the constant rain of cosmic rays and other distracting particles, creating a silent, dark laboratory where only the most penetrating particles, the neutrinos, can reach. The detectors themselves are monumental. Imagine a cavern filled with a gigantic, perfectly transparent tank containing 50,000 tons of ultra-pure water or a special scintillating fluid. The walls of this tank are lined with thousands of incredibly sensitive light sensors called photomultiplier tubes. The entire apparatus operates in complete darkness, waiting for the 1 in a trillion event where a neutrino, against all odds, actually strikes an atomic nucleus within the liquid. When this rare interaction occurs, it can produce a faint, faster-than-light flash of blue light known as Cherenkov radiation, or it can transform into another particle, like an electron or a muon, that then streaks through the detector. The surrounding photomultiplier tubes capture this faint glimmer of light, and by analyzing its timing and pattern, scientists can determine the neutrino's energy, direction, and even its type, tracing its path back to its cosmic source. The scientific payoff for this painstaking work is revolutionary. Neutrinos are allowing us to see the universe in a completely new light, literally. They give us a direct view into the hearts of stars and the cataclysmic violence of supernova and merging black holes. They are helping us solve fundamental mysteries about the nature of matter itself, such as why the universe is made of matter and not antimatter. We now know that neutrinos oscillate, meaning they can spontaneously change their identity between 3 different types: electron, muon, and tau neutrinos as they travel. This discovery, which won the Nobel Prize, proves that neutrinos do have mass, however slight, challenging and refining the standard model of particle physics. Giant detectors like IceCube at the South Pole, which uses a cubic kilometer of deep Antarctic ice as its detector medium, are even searching for ultra-high-energy neutrinos from the most powerful objects in the universe, like active galactic nuclei and gamma-ray bursts. These ghostly particles, once thought to be nearly impossible to detect, have become one of our most valuable tools for probing the hidden workings of the cosmos, revealing a universe that is not just seen, but felt through these silent, streaming messengers from the abyss. While the motions of individual stars and the slow evolution of our solar system operate on their own grand timescales, the very galaxy we call home is itself on an unstoppable collision course with a cosmic neighbor. In the constellation Andromeda, there is a faint, fuzzy patch of light visible to the naked eye on a clear, dark night. That smudge is the Andromeda Galaxy, the closest major spiral galaxy to our own Milky Way, a collection of roughly 1 trillion stars. For centuries, we saw it as a permanent, distant island in the void. But in the early 20th century, astronomer Vesto Slipher measured its light and found it was shifted toward the blue end of the spectrum. This blue shift was the first clue that Andromeda was not static. It was moving toward us. Decades later, with more precise measurements from the Hubble Space Telescope, we confirmed the astonishing truth. The Andromeda Galaxy and the Milky Way are gravitationally bound in a mutual fall, set to collide and merge in an event of unimaginable scale about 4.5 billion years from now. This is not a speculative possibility. It is a calculated certainty, the inevitable outcome of the gravitational pull between these 2 cosmic giants over billions of years. So, what would this epic event look like from the perspective of a hypothetical future Earth? The process is not a sudden, explosive crash, but a long, drawn-out, and majestic dance that will unfold over billions of years. For a very long time, nothing would seem to change. But in about 2 billion years, if any life remains on our planet to look up, they would begin to notice Andromeda growing progressively larger and brighter in the night sky. Over the next few billion years, it would swell from a faint smudge into a spectacular, sprawling band of light, eventually rivaling and then surpassing the brightness of our own Milky Way. As the galaxies draw closer, their immense gravitational forces will begin to warp and tear each other apart. Long, graceful streams of stars, gas, and dust will be pulled out into vast tidal tails, creating a celestial tapestry of intertwined filaments that will dominate the entire heavens. The familiar band of our Milky Way would become distorted and mingled with the incoming structure of Andromeda, creating a chaotic, breathtakingly beautiful sky filled with two interpenetrating spiral patterns. When the two galactic cores make their first close pass, they will not directly hit each other. The vast distances between stars mean that actual stellar collisions are extraordinarily rare. The galaxies are mostly empty space, so our solar system would almost certainly survive this first encounter intact. However, the serene stability of the night sky would be utterly shattered. Instead of a single, dominant Milky Way, the sky would be a riot of structure with glowing nebulae, star clusters, and brilliant new star-forming regions ignited by the compression of interstellar gas. The orderly spiral arms we know today would be stretched and twisted beyond recognition. After this first pass, the two galaxies, still locked in gravity's embrace, will swing apart and then fall back together for a second, closer encounter. This gravitational tug-of-war will continue, with each pass transferring energy and pulling the galaxies into a tighter, more chaotic embrace. Over the course of another 1 to 2 billion years of this cosmic dance, the two spiral galaxies will lose their distinct shapes entirely, their stars becoming scattered into a vast glowing cloud. The final product of this multi-billion-year merger will be a single, giant, featureless elliptical galaxy, which astronomers have already given a name, Milkomda. The fate of our solar system within this cosmic maelstrom is a subject of intense study. While direct star-to-star impacts are unlikely, the gravitational perturbations are not. Our Sun, along with its planets, could be flung out into a much larger, more distant orbit around the new galactic center, or even ejected entirely into the lonely intergalactic void as a rogue star system. Alternatively, we could be drawn inward toward the bustling core of the new galaxy. The one near certainty is that our position in the galaxy will change dramatically. The formation of Milkomda will trigger a final, brilliant burst of star formation as the remaining gas clouds collide, but this will be followed by a long, quiet senescence. Once the gas is used up or blown away, star birth will cease, and the new galaxy will gradually age, its stars burning out one by one over trillions of years. This galactic collision is not a unique catastrophe, it is a standard part of galactic evolution. We see merging galaxies throughout the universe, and our own fate is simply a local example of this universal process. The knowledge that our entire galaxy is on a collision course reshapes our perspective, reminding us that even the largest structures we can see are not permanent, but are dynamic participants in an ever-changing cosmic ballet that plays out over timescales we can barely comprehend. Yet, even as we map the gravitational pull of a potential planet 9 and anticipate the distant collision with Andromeda, there exists a phenomenon on the very edge of our cosmic maps that challenges our understanding of the universe's fundamental structure. This mystery is known as the dark flow, a term that evokes a sense of a hidden cosmic river, and it describes a controversial observation that some massive galaxy clusters appear to be drifting in a coordinated, unexpected direction, as if being pulled by something immense that lies entirely beyond the horizon of our observable universe. The story begins not with a visible object, but with the fossilized light from the universe's infancy, the cosmic microwave background. This afterglow is not perfectly uniform. It contains tiny temperature variations that serve as a cosmic reference frame. As enormous galaxy clusters travel through space, they interact with this radiation in a specific way through a process called the kinematic Sunyaev-Zeldovich effect. Essentially, the hot gas within these clusters scatters the microwave background photons, and by studying the subtle shift in the energy of these photons, astronomers can measure the cluster's velocity relative to the fundamental rest frame of the cosmos. When a team of scientists led by Alexander Kashlinsky analyzed data from the Wilkinson microwave anisotropy probe and later the Planck satellite, they found something startling. Hundreds of distant galaxy clusters scattered across billions of light-years seemed to be moving in a coordinated stream at velocities of over 600 miles per second toward a specific patch of sky between the constellations Centaurus and Vela. This motion was in addition to the overall expansion of the universe and could not be explained by the gravitational pull of any known supercluster or cosmic structure within our observable realm. It was as if these colossal islands of matter, each containing thousands of galaxies, were all being tugged by a force originating from a region of space we cannot see. This discovery immediately ignited intense debate within the cosmology community, as the implications are profound. The standard model of cosmology, which includes the Big Bang and dark energy, is built on the cosmological principle, the idea that on the largest scales, the universe is homogeneous and isotropic, meaning it should look roughly the same in all directions and no single direction should be preferred. The dark flow, if real, appears to violate this foundational principle. It suggests an anisotropy, a cosmic lopsidedness on the grandest possible scale. What could possibly be exerting such a vast, coordinated gravitational pull? One of the most mind-bending hypotheses is that the flow is evidence of the gravitational influence of a region of space-time that lies beyond our cosmic horizon. Our observable universe is a sphere about 93 billion light-years across, representing the distance light has had time to travel since the Big Bang. But the entire universe is likely much, much larger, possibly infinite. The dark flow could be the first indirect evidence of this greater structure. The mysterious pull might be coming from a supermassive concentration of matter, another galaxy supercluster, or a vast, exotic structure of a kind we've never seen, that formed in a neighboring region of the greater cosmos during the initial moments of inflation. Because this region is beyond our cosmological horizon, its light has not had time to reach us and will never reach us given the accelerating expansion of the universe. Yet gravity, according to our current understanding, may be able to exert its influence across this divide, meaning we are feeling the gravitational tide of a part of the cosmos that is forever invisible to us. Of course, a claim this extraordinary faces rigorous scrutiny, and the scientific debate is far from settled. Skeptics have proposed several alternative explanations that do not require physics beyond the standard model. One significant challenge involves the data itself and the complex methods used to extract the velocity signal. The kinematic Sunyaev-Zeldovich effect is an extremely subtle measurement, and it is possible that foreground emissions from within our own galaxy or systematic errors in the analysis could be creating a false signal that mimics a coherent flow. Some researchers have attempted to replicate the finding with different methodologies or newer data sets, such as those from the Planck mission, and have reported either a much weaker signal or no detectable flow at all. The precision required is staggering, and isolating the specific signature of the cluster's motion from all the other competing signals in the cosmic microwave background is a monumental task. Another possibility is that the flow, while real, is not a sign of something beyond our horizon, but rather the lingering effect of a primordial giant fluctuation, a rare, enormous irregularity from the universe's first moments that has imprinted a large-scale motion on a vast swath of the cosmos we can observe. However, the sheer scale and coherence of the observed flow make even this explanation challenging within our current models of cosmic evolution. The ongoing investigation into the dark flow represents a thrilling frontier in cosmology. It is a powerful reminder that our map of the cosmos is still incomplete and that the most profound discoveries often lie in the anomalies, the data points that stubbornly refuse to fit our established theories. Whether the dark flow is ultimately confirmed as evidence of a neighboring super-universe or explained away as a complex systematic error, the journey of its investigation pushes our observational techniques to their absolute limits and forces us to question our most basic assumptions about the nature of reality. It invites us to consider that our entire observable universe, with its hundreds of billions of galaxies, might be just one small part of a far vaster and more complex structure, a single piece in an infinite cosmic quilt, whose other pieces we can only sense through the faint, ghostly tug of their gravity. And while our own planet crackles with spectacular electrical storms, they pale into insignificance when compared to the apocalyptic fury raging within the atmosphere of our solar system's giant. Imagine a single flash of lightning so immense that it releases more energy than all the lightning strikes on our entire world combined in a given moment. This isn't science fiction, it is the reality on Jupiter, where the Juno spacecraft has detected bolts of such staggering power they defy earthly comprehension. We often picture lightning as a brilliant, forked streak illuminating our skies, a powerful but relatively localized phenomenon. On Jupiter, the scale is different. The lightning there is hundreds, and at times thousands, of times more energetic than the most powerful superbolts ever recorded on Earth. Some of these Jovian discharges pack the energy equivalent of several atomic bombs, a single, instantaneous explosion of electrical force that dwarfs the cumulative output of every thunderstorm happening across our globe at once. This immense power arises from a perfect storm of atmospheric conditions that make Jupiter a truly electric planet, a world where the very fundamentals of weather are amplified to an almost unimaginable degree. The key to understanding Jupiter's monstrous lightning lies in its fundamentally different atmospheric composition and the sheer scale of its weather systems. On Earth, thunderstorms are driven by the upward motion of warm, moist air. Water vapor rises, condenses into clouds, and the complex interactions between ice crystals and water droplets within these clouds separate electrical charges, building up the tremendous potential that is eventually released in a lightning strike. Jupiter's recipe for lightning is similar in principle but vastly different in its ingredients. While the planet's upper clouds are made of ammonia ice, scientists believe the powerful lightning originates much deeper in the atmosphere, in clouds believed to be composed of water and ammonium hydrosulfide. Here, the convection is not powered by the sun's warmth on a surface, as Jupiter has no solid surface to speak of, but by the colossal heat welling up from the planet's scorching interior. This internal furnace drives convection on a scale that makes Earth's largest hurricanes look like gentle breezes. Gigantic plumes of warm, moist air, or more accurately, a humid mixture of gases, can rise tens of thousands of miles through the Jovian atmosphere, creating towering thunderheads that make our tallest cumulonimbus cloud seem minuscule. Within these unimaginably vast storm cells, the churning and collision of different types of ice crystals, water ice, ammonia ice, create titanic charge separations, building up voltages that are simply not possible within our planet's comparatively shallow and less energetic atmosphere. This is where NASA's Juno mission has been revolutionary, providing our first clear look at these deep, powerful bolts. Previous spacecraft like Voyager had detected radio signals suggestive of lightning, but they could only observe the flashes high up in the atmosphere, which were relatively faint. Juno, with its suite of advanced instruments designed to peer deep into Jupiter's gaseous envelope, revealed a different story. Its microwave radiometer and WAVES instrument have detected the low-frequency radio emissions known as whistlers that are the unmistakable signature of lightning. Crucially, Juno found that the most powerful lightning activity is concentrated near Jupiter's poles, a stark contrast to Earth, where lightning is most common in the tropical regions around the equator. This polar preference points directly to Jupiter's unique energy balance. At the equator, the planet receives most of its external energy from the sun, which stabilizes the atmosphere and suppresses the large-scale vertical convection needed for the biggest storms. But at the poles, which receive less solar energy, the atmosphere is more free to churn based on Jupiter's own internal heat. This allows the massive convective plumes, fueled by the planet's interior furnace, to rise unimpeded, creating the perfect incubators for the most powerful electrical storms in the solar system. Some of these flashes are so brilliant that amateur astronomers have occasionally captured them from Earth with large telescopes, appearing as fleeting, bright points of light against the dark backdrop of Jupiter's belts. The raw power of this lightning has consequences that extend far beyond the momentary flash. Each colossal bolt is a natural particle accelerator, and the tremendous energy released can break apart the simple molecules like methane and ammonia that are abundant in Jupiter's atmosphere. This process, known as dissociation, creates highly reactive atoms and molecular fragments that can then recombine into new, more complex compounds. In essence, Jupiter's lightning is constantly performing a form of atmospheric chemistry, acting as a planetary-scale spark plug that may be responsible for generating some of the more complex carbon and sulfur-based molecules that give the planet its distinctive colors and banded appearance. While it's a hostile and violent form of chemistry, utterly different from the gentle, water-based reactions that led to life on Earth, it demonstrates a fundamental principle: energy input can drive complexity. The continuous electrical bombardment within Jupiter's storm cells is a testament to the raw, transformative power that exists within gas giants, a power that shapes not just their weather, but their very chemical identity. So the next time you witness a thunderstorm lighting up the night sky, remember that it is but a faint echo of the celestial fireworks happening 500 million miles away, where the King of Planets unleashes electrical fury on a scale that truly defines the word astronomical. It's a striking thought, isn't it? After all the incredible discoveries we've explored, from the violent lightning of Jupiter to the ghostly pull of the dark flow, one final fact brings our journey full circle in a truly profound way. It's a story not just about what is out there, but about our very act of looking, and how a single, daring gamble to stare into apparent nothingness forever changed our cosmic perspective. This is the story of the Hubble Deep Field, a picture that is arguably one of the most important ever taken, not for its beauty, though it is beautiful, but for the monumental truth it pulled from the void. In the mid-1990s, a team of astronomers at the Space Telescope Science Institute, led by Robert Williams, faced a unique problem. The Hubble Space Telescope, after its repair mission, was working perfectly, but a fundamental question lingered: what was it truly capable of seeing? To push its limits, they proposed a radical and, to some, a deeply wasteful idea. They decided to point the most expensive and powerful telescope ever built at a patch of sky that was, by all previous accounts, completely and utterly empty. The chosen spot was a tiny, dark sliver in the constellation Ursa Major, a region carefully selected because it was devoid of any bright stars from our own galaxy, any known distant galaxies, or even any nearby asteroids that might leave a trail. It was, for all intents and purposes, a cosmic blank canvas, a piece of celestial real estate that seemed to contain absolutely nothing at all. The plan was audacious: to keep Hubble's gaze locked on this single, empty point for 10 consecutive days, an unthinkably long exposure that would soak up every possible photon of light, no matter how faint. Many in the astronomy community were skeptical, arguing it was a reckless gamble of precious observing time that would likely yield a photograph of pure, featureless black. But Williams and his team persevered, believing that if there was something to be found in the deepest dark, Hubble was the instrument to find it. When the data finally finished downloading and the team began to process the image, the result was so astonishing that they initially suspected a technical error. The blackness had come alive. The field was not empty. It was crammed, jam-packed with a breathtaking array of fuzzy, multicolored smudges. They weren't looking at blank film. They were looking at a universe they never knew existed. Each one of those smudges, and there were nearly 3,000 of them in that single tiny frame, was an entire galaxy. The Hubble Deep Field revealed a universe teeming with galaxies as far as the telescope could see, a cosmic core sample drilled deep into space and time. The variety was staggering. There were majestic spiral galaxies similar to our own Milky Way, but seen in their turbulent youth. There were massive red elliptical galaxies, the ancient retired giants of the cosmos. And there were countless irregular, peculiar galaxies caught in the act of violent collisions and mergers, their shapes stretched and distorted by gravitational interactions. This one image was like a time machine. Because light takes time to travel, the most distant galaxies in the frame were being seen as they were when the universe was less than 1 billion years old, a mere toddler compared to its current age of 13.8 billion years. The profound implication was immediate and inescapable. If a random, seemingly empty patch of sky, a fragment no larger than a grain of sand held at arm's length, contained thousands of galaxies, then the entire observable universe must be filled with an almost innumerable quantity of them. The estimate skyrocketed. Suddenly, we understood that there were not simply tens of billions of galaxies, but likely hundreds of billions, perhaps even 1 to 2 trillion galaxies in the cosmos we can observe. But the true legacy of the deep field wasn't just the staggering number. It was the story it told about the history of the universe itself. By cataloging the galaxies by their shape, color, and distance, astronomers could construct a visual timeline of galactic evolution. The image showed a clear progression from the small, fragmented, and blue building blocks in the early universe galaxies bursting with the fiery birth of new stars, to the larger, more structured, and redder galaxies that had matured over billions of years. It provided direct visual evidence that galaxies grow over time, through a process of merging and cannibalization, slowly assembling into the majestic spirals and ellipticals we see in our cosmic neighborhood today. The success of the original deep field was so monumental that it spawned an entire family of even deeper looks into the cosmos. The Hubble Ultra Deep Field, observed in 2003 and 4, stared for 1 million seconds to peer even further back in time, capturing galaxies that formed just 400 to 800 million years after the Big Bang. Then, in 2012, the E-Extreme Deep Field combined 10 years of observations to create the deepest infrared view of the universe ever, revealing the first galaxies to emerge from the so-called Dark Ages, a time when the first stars and galaxies were just beginning to ignite and flood the universe with light, ending the cosmic dawn. Each of these follow-up observations confirmed and deepened the initial revelation, painting a picture of a universe that is not just vast, but intensely active and evolving, a cosmic ecosystem where galaxies are born, mature, and interact over the eons. The Hubble Deep Field did more than just fill a blank space in a photograph. It filled a void in our understanding. It gave tangible, visual proof to the abstract numbers of cosmic scale, transforming our place in the universe from a central one in a modest collection of galaxies to an utterly insignificant one in a near-infinite ocean of island universes. It was a testament to human curiosity, a reminder that the greatest discoveries often await not where we know to look, but when we have the courage to point our most powerful instruments at the apparent emptiness and simply ask, what if? And so our journey through the hidden cosmos draws to a close, but what a spectacularly strange universe it has revealed. We began with the silent, slow farewell of our own moon and traveled to the heart of a galactic distillery brewing alcohol across billions of miles. We stood in awe of a planet where the sky rains molten glass sideways and contemplated entire worlds forged from diamond. We felt the crushing density of a neutron star where a single teaspoon weighs 1 billion tons and listened to the haunting songs of planets and the deep, resonant hum of the Big Bang itself. We've witnessed the fleeting, brilliant spectacle of Saturn's youthful rings and the colossal, ancient storm of Jupiter that is slowly fading before our eyes. We've grappled with the mind-bending reality that time itself is fluid, warped by speed and gravity, a truth that powers the very GPS in your pocket. From the vast, silent emptiness of the Boötes void to the chaotic dance of planets with twin suns, and from the ghostly stream of trillions of neutrinos through your body to the impending, majestic collision of our Milky Way with Andromeda, every fact has peeled back a layer of the ordinary to reveal the extraordinary lurking just beneath. We've even discovered that the center of our galaxy holds the flavor of raspberries and that stars ring with their own unique music, if only we know how to listen. These 30 glimpses are not just a collection of trivia, they are a testament to a cosmos that is vibrant, dynamic, and infinitely creative, a place where the laws of physics conspire to create wonders far beyond the scope of any schoolroom lesson or science fiction novel. It is a universe that is not merely large, but deeply, profoundly alive with possibility and mystery. Now we turn the conversation over to you. With so many mind-expanding realities to choose from, which of these facts reshaped your understanding of the cosmos the most? Was it the planet with supersonic winds of glass, the ancient water ice hiding in the scorching shadows of Mercury, or the existential scale of the Hubble Deep Field revealing billions of unseen galaxies? Let us know in the comments below. We are genuinely excited to hear which cosmic truth captured your imagination. If this voyage into the unknown has left you hungry for more, be sure to subscribe and hit the notification bell. Our channel is dedicated to pulling back the curtain on the universe's greatest secrets, from the enigmatic nature of black holes and dark matter to the ongoing search for life beyond Earth. The adventure is just beginning, and there are countless more cosmic revelations waiting to be discovered right here. Thank you for joining us on this incredible expedition. Keep looking up and never